anniversary event. So we're going to meet virtually in the next 3 days, it's great to see a lot of people who've been around for either a long time or less time. Indeed, this anniversary, 60 years, puts me about in the same generation. And I started as a young engineer in the gas industry with people around me working on the GERG equation of state, and then also on other projects. I was also personally involved in some of these projects, one on gas leaks in soil and others. So I think this is really one of the oldest initiatives where the industry got together to develop research collaboratively, and I'd invite David, one of the past presidents, to see us a little bit around or through the 60-year history. And once again, welcome everyone. We will have this, as you can see from the agenda. You will have the retrospective by David. Then we will have a glimpse at how GERG is structured today. We started as an association covering a very wide variety of R&D challenges. Now we're focusing also on many challenges, but around 3 teams. And today's, so the 3 days will reflect those 3 themes. And today it's all about methane emission reductions. Tomorrow will be biomethane and hydrogen on Friday. So David, over to you.
Thank you very much. And it's a great pleasure to be here at the 60th anniversary of GERG. And I was very fortunate to be at the 50th anniversary. And sorry, can you hear me okay? Yeah. So can we mute the other lines? Okay. Thanks. Yeah, great pleasure to be here. And as I was at the 50th anniversary, and I took over as president shortly after, and was president of GERG for about 6 or 7 years. I've just come back from Australia, where I was working in the electricity industry as the asset manager and executive responsible for engineering at a company called Essential Energy, who run the electricity network in New South Wales. And one of the things that was just emerging as I was leaving Australia was hydrogen, power to gas, and Australia's picked it up in a pretty big way. So it's good to see that the things we started talking about years ago are affecting the world worldwide. So let's look at where we were with GERG. It was formed in 1961. If we move the slide forward. Who's driving the slides? Yes. So 1961. I see we've got a picture of our current Secretary General in the bottom right hand corner. Fortunately, there were no pictures of me in 1961. So I don't go back quite that far, but there was a lot happening in 1961. Yuri Gagarin, first human in space. John F. Kennedy. The death of Schrödinger, but who can tell because he's in a box. He may still be alive, we never know. So a long time ago, and a long far way away. But it marked the transition. Oh, I can hear myself back. It marked the transition of the gas industry from Towns gas to methane. So if we look at 1961, next slide. GERG was formed by 5 companies, by British Gas, Gaz-Uni, Ruhrgas, Gaz de France, Snam, and formed as an organisation to share research aims and to help with the fundamental understandings of what it would take to transform the gas industry. Now in 2021, I think there's 27 members or more across many more countries, and the ability to work together to enact the next transition that we go to. So some of the things that GERG has been responsible for, if we go to the next slide. So it was formed during that transition from, as I say, from Thames gas to natural gas. And it was really a thing so that, you know, everyone needed the same answers so they could share the costs and share the risks and share the expertise to be prepared for new challenges and get to the answers that would help them in that transition. So the first GERG projects were catalysts for the production of Thames gas and methane, odorization, and burners for the combustion of Thames gas and natural gas. So right on the energy transition subject. Move forward again. So some of the things that GERG has been responsible for or helped facilitate, gas detection by cameras. Yes, without GERG, you'd still be having your noses to the ground and smelling gas coming out of the ground. I think there were other ways of doing it as well, but that one is quite hilarious. Go forward, low NOx gas burner development. So, you know, making some real inroads into reducing harmful emissions. As we've already discussed, the change of the equations of state, and the GERG equation of state is the best in class. So, you know, some really good developments as a result of this organisation existing. One I particularly liked while I was president was the LNG densimeter. So being able to calculate the calorific value of a shipment of LNG, therefore the cost accurately and quickly was a very, very important development. Keep moving forward. We've got perturbation effects of ultrasonic meters and fundamental research to make sure that, again, we're calculating volumes and values correctly or as accurately as we can. And then move forward to a really fundamental change for the industry, which was the introduction of polyethylene pipe, and, you know, moving away from metallic materials underground. That truly is a set of developments that have revolutionized the way networks are developed and run. And going forward, just one more, satellite surveillance of the transmission system. So the ability to detect changes in and around pipeline routes from satellite and be able to understand the risks associated with that is a huge step forward from, you know, flying by helicopter every couple of weeks and hopefully intervening with people who are in the wrong place with the wrong equipment, put it that way. So really, really good developments. But I think one of the things that that GERG has done, which has been really most fundamental to the next energy transition if we move forward, is really the story around power to gas and gas to power, and the development of standards around hydrogen and telling the story of the need for a hydrogen economy for a couple of reasons. One is you know, energy storage, and batteries aren't really going to cut it when it comes to the volumes of energy storage you need to get through the night and to get through the winter, and also the sheer amount of energy that currently goes through the gas grids, and the thought of transferring that to the electricity networks is just in the northern hemisphere is just an extreme level of change that could be better managed through the adoption of hydrogen. So yeah, fundamental work by GERG, and I'm sure we'll hear more of that over the next couple of days. Next. Gas quality, gas interchangeability, other standards that have been produced, appliances and other work that's fundamental to the safe operation of the network has been done under the banner of GERG. And if we move forward, support to young researchers. I particularly liked it in my time as president, handing out awards for young researchers and hearing and reading the work that they've done in and around the gas industry. It's a pleasure to bring forward the next generation, and GERG has always played a massive role in providing an academic research network and an outlet for people to show what they've done and what they're capable of. So I think that's a great development that long should continue. So just to conclude, GERG was formed at a time when fundamental research was needed to transition an industry. And it's continued for 60 years, since 1961, and the time has come again when there's a need for a fundamental shift in the industry, and GERG stands ready and committed to supporting that fundamental collaborative research across multiple parties in multiple countries. Collaborative research is vital. You've got to share the costs, you've got to share the expertise, and you've got to share the results. There is no competition element within this. This is about maintaining the safety of the industry and preparing the industry together for the future. So I think the GERG model is ready to take the industry to the next phase. It's interesting that Rob reminded me this morning that GERG actually moved to Brussels about 25 years ago from Apeldoorn. So it's the 25th anniversary of that move, as well as the 60th anniversary of the organisation. And I think, I personally left GERG in a better place than I found it, and it seems to have continued to grow and move from strength to strength. So with that, I'll conclude and hand over to the current president, who will take you forward to what comes next.
Thank you very much, David, and I'd like to to thank you for all these years where you helped push GERG forward. And as you mentioned, there's a new energy transition underway that is very disruptive, and let's see how GERG adapts to this. Next slide, please. Indeed, while you've seen that with the rest many things, and over time, as GERG mentioned, GERG is now a lot stronger with members from operations, operators, also operators associations, but also friends of GERG who are consultants or other industry, other segments of the industry that work for the energy pipelines and energy networks, as well as very significantly famous academic institutions. So all this is now more than about 35 members. So that's a significant network that also, as you can see, networks with other international organizations like PRCI, also from Australia, APGA and Future Fuel CRC, the US, not only PRCI, but also GTI, and most importantly, very well rooted in the European arena with FCHGU, CEN, GAE, Marcogas, also Hydrogen Europe, and many others. So indeed, it's all about coordinating with the different players and bringing each the new elements together so that we can build up in this uncertain future a place for the gas networks to continue providing energy supply, security of supply, and being complementary to power. So it's clear that in the decarbonization trend, new challenges. We have identified 3 strategic priorities and organized those along 3 working groups. As you can see, decreasing methane emissions, bringing hydrogen into the energy mix, and also greening the gas with biomethane, and with their corresponding vice presidents, Bernice, Tanguy, and Torben. While the program committees that have always been at the core of GERG are there to implement the projects that are defined in the roadmaps being set up in the 3 working groups for the strategic priorities. Obviously, the Secretariat and Robert and his team are essential to operating GERG efficiently. We have Alexandra, Magdalena, and Miguel. Many thanks to them. They support Robert very effectively. And obviously, all this is supervised by the board with the 3 vice presidents, Christian, Anthony, and Bernice. So obviously, what this is all about is to set up projects and then produce the results. So next slide, please. That can be then disseminated into to the industry, to our members and the wider community. So as mentioned, in order to clarify, prioritize our activities, we're setting up research roadmaps that on the 3 strategic topics. And we started with the brainstorming phase where we gathered, sorry, I have a severe cold. We brought GERG members, interacted with the wider industry professional experts. We defined the research topics and I would say put them in perspective, both in terms of quick wins and longer term changes, and ended up producing the roadmaps that will help developing projects to be performed as mentioned in the GERG program committees, but also to interact with the other organizations and coordinate so that there's no overlap and that there's a good way to exchange information and accelerate progress. Next one, please. So I think it's interesting that in this anniversary we can share now for the first time publicly outside the working group circle and the very dedicated people who brought this all to life with the support of the Secretariat, 3 roadmaps on the 3 topics. So today on methane emission reduction, tomorrow on biomethane, and on Friday on hydrogen. And that's why I invite you to now start the session on today's priority, which is reducing methane emissions. And I hand over to Bernice, who will tell you about our roadmap. Thank you very much.
Thank you, Miris. Indeed, today will be about methane emissions, management of methane emissions. As you know, this is a very important topic. It is a research priority of GERG, as Miris explained this very well to you. And it must not be a surprise that this is a research topic for us and a priority. Alexandra, if you could give the next slides, please. Next one. Indeed, because if I would quote what certain people are saying, it's for the moment something which is very hot and a very hot topic, and it's really in the spotlights, because really being able to reduce methane emissions is today an important way to reduce global warming. So it has been identified by different people and authorities as being an important thing to work on. Well, we know that the European Commission is working on a legislation about it. We are expecting something for 14th of December. So we know that there will be talking about reducing methane emissions, and especially measure, report and verify this. So we are really waiting for this text to come out, but it's not the only one, because it was one of the subjects that was spoken of at Glasgow at the COP26. We know also that at the G20 summit, there was the launch of the International Methane Emission Observatory, the IMEO, and a lot of countries has also made a pledge to reduce methane emissions by at least 30% from 2020 to by 30% by 2030. So it is really an important subject. It's a really hot subject, and we are working on this with GERG. This is not a surprise neither, because in fact, methane emissions, we have been working on it as a sector, as gas companies and operators since a very long time. Because finding methane emissions, finding leaks, has always been an important subject for operators, network operators, for example, because it was linked to safety. And so we have, it's something that in Europe and in especially also in cities, finding leaks was important for the safety. So we have already worked on that. It's not a new thing. But on the other hand, we were more focused on finding the leaks than on measuring them, because it was less important. It was more important to find them. So we still need research. We still need innovation, because now we need also to do more quantification, reporting, which is more, I would say, something more new. So we have already worked in the past on new technologies, but we want to continue to innovate, look for the best technologies, also for the ones that are most cost effective, because as it is also important, cost effectiveness of different measures it will be important. It's important today, but it will remain important in the future. And in all those efforts to make the energy transition a just transition, which is affordable for everyone. So innovation is central. So we, as GERG, we still have an important role to play in this field. Next slide, please. So when we look at methane emissions, the question is, how can we manage them? So methane emissions is, we have been making a model on those methane emissions, and it is important, in fact, to look at how can we detect, how can we mitigate, but also how can we use it in a loop to continuously improve the methane emissions management. And this will be also different for each element, I would say, in the energy value chain. Each sector, transmission, production, distribution, are all different. We all have our own specific challenges that are on technological or operational sides, and it's important that we take these elements also in account in making the best, looking for the best ways, the most cost-effective ways to mitigate methane emissions. So we've been looking at a model. Alexandra, please, next slide. And it's not it's not so readable on a slide, but I think it's more important to see that we've been trying to look at all the elements which are important in methane emission management. The first one is, of course, the identification of the emission sources. It's different from type of assets. Type of emissions are also different because you can have fugitive emissions. You can also have emissions that are linked to incomplete combustions, and it's also activity factors are also an important element. So first one is really identify the emission sources. Then once you have made the sources inventory, is looking at your leak detection and repair. This is the loop. I would say that's the loop that you have to cover. So the first thing is when you have them, you have to find or to define measurements and quantification campaigns. This here, I would say that's really an important thing now. It's how to measure how much methane you have really emitted. Of course, then there are different ways. If you're going to measure different ways to do it, you have what we call the bottom-up technologies. That is what's being measured on site. But you have also top-down methodologies, how you can measure it on another way. And of course, the important thing is to reconcile those results, because of course they're not the same as the different method says different uncertainties, and I would say this is really an important element also in the research and research roadmap, is not only which technologies but especially which uncertainties these different technologies have, which and especially difficult to in the reconciliation. So this is really important, and really elements we have to focus on the research map. On the other hand, you have also the emission factors, and it's something we've already worked in the past, but it's really very important to have those emission factors, because it's not always possible to measure. So working with good emission factors is something which is very useful and can be also very cost effective. When you bring all this together, of course you have to, this is an important, I would say this is the measurement part. Then comes the next part, which is the reporting, which is also important. And then you have the verification. You have to have this verified. And of course, this is a loop, because when you have all this, you're going to look also at your operational practices. You can, based on excuse me, based on this also, you can look at your operational practices. And what you can do also is identify the best available techniques. Which can help you to reduce the methane emissions. And then of course the cycle begins and goes back to the top, and you start again to look and identify emission sources. So this is really, I think, when looking at methane management, these are the elements of the cycle you have to do, you have to go through to get to be in a position to manage those methane emissions. Next slide, please. And so, as Marez already said, we have been working for the different research priorities. We have been working on a roadmap. This roadmap was a collaborative effort. We've worked with industry experts. We've also worked with other organizations. Here I want to thank Marcogas, because we worked a lot with the experts of the different working groups in Marcogas, and I want to thank them for the work together. And it was, we looked at it from, I would say, from different point of views. We looked at it from the different activities in the value chain. of course, it is different, and as I said before, the operational challenges are different in the different segments of the value chain. Distribution is different from transmission, is different from utilization, and biomethane is certainly also an important element here in this value chain, and also has to be, the methane emissions from biomethane production also have to be tackled. On the other hand, we, based on our cycle that I explained in before, we have been looking at elements of detection, of quantification, of mitigation. For all these elements, we have been looking at what is the basis of the emissions roadmap. We've been looking at gaps. Which are the gaps? What do we need? Where are still the gaps? What do we need to know more about? And this is also the basis to go and identify precise research actions and also possible projects we can do. Of course, not all are as critical. Some are more, I would say, important, or you have to act on them quicker than other ones. And of course, we have been looking also at criticality, at urgency, in order to really look at priorities. Next slide, please. And if I look now at key findings for our different roadmaps, when we look at transmission and distribution, we have also different elements for LNG, and also for utilization and biomethane. But if we look now for transmission and distribution, I think the research actions, the first one is the different detection and quantification techniques. Finding, as I already told you before, reconciling data from different sources, validating new technologies is, I think, one of the most important things. And we have already been working on those ones, and you will see what we have already done in next presentations. But I think this is one of the most important elements. Then correlation factors. It is also very important. Improved correlation factors, because it's this is also important. We will not be able to measure everything at every moment. It's really depending on the operational conditions, and so it's important to demonstrate those correlation factors. Then the third one is emission factors. It is, I think, and it stays for me. For me personally, it stays one of the important elements, and developing a European database would be a very important research topic and a very important project for the future. Now, having a better knowledge on activity factors, leak site distributions is something also very important, because we could better target emission reduction measures. And mitigations, the best practices is still the same. It's something that can be very useful for operators to know those best practices, because it is really important to do it on an efficient and cost-effective technologies. I'm really insisting on this element, because it is important that we could use the best technologies to reduce methane emissions, and cost is and stays an important factor. Now, if we look at LNG, their best practices, to be able to share them for LDAR campaigns and emission factors is something which is important for LNG sites. Mitigation actions also, because this is a very specific operational situation, and limitation of emissions from the different activities within an LNG terminal can be very much important, but not only the terminal itself, but also the truck loading and flaring best practices. This is important for the value in LNG as element of our value chain. Next slide, please. Then we have also looked at other elements in our value chain, which are utilization and biomethane. For utilization, it is, in fact, I would say we want to know more about the existing emissions. So there is a need for gathering more data from the field, like emission factors. But also, if you, it's also important if you test that, if you want to assess emissions, that you develop test protocols. And this is also something that we identify as a research action in our roadmap. And a third element is if you have engines and incomplete combustion, that can be also one of the methane emissions sources. And so if we better can mitigate those incomplete combustion, this can also be an important research topic for roadmap. If we look at biomethane, there it's in fact what's important to know. It's biomethane is of course a very important factor, and we will be talking about it tomorrow on biomethane. It's a research topic on itself, but of course, and it's a potential to have negative emissions, the biomethane sector, but it's important to have a life cycle analysis of the emissions from the biogas and biomethane sector. So this can be a very important research topic and a research priority too. Of course, emission factors, you will not be surprised, as this is, you'll find it in the different elements of the value chain, but it's also important for biomethane. So finding them, defining them through measurement campaigns is I think, one of the important elements also in the research roadmap. And also plant operators are interested in have more kits. I would say it's really to give them some kind of help of how to survey the plants, how to find those how to manage those methane emissions coming from the plants, and developing survey kits would be also a very interesting and a very important research action. And best practice, it's also something you find in different elements in the different value chain, but best practice methods is also important for the biomethane sector. And overarching, I think this is also a very important element, is those cost abatement curves per value chain segment. This is for me also a key element. As I said it before, for me, finding the best cost-effective ways to reduce methane emissions for the different elements of the value chain, and it will be different for the different elements of the value chain, is really key for in the coming years. As you know, it is completely in what the European Commission is saying about those energy transition. We have to make it a just transition, and this means that we have to think about also about people who can't afford energy and energy poverty. So this is an important element. So we have to do this important thing to reduce methane emissions, reduce greenhouse gas emissions, but do it as a most cost effectively as possible, because this is impacting tariffs, this is impacting everything. So it's important that we also look at it from a research point of view. Next, please. So I'm reaching here my conclusion slides. Yes, in fact, it's new and not new. This research that we're doing on methane emissions is of course a new elements, and we bring new topics to the table. But it's not new, as we have been working since a long time on efforts to limit and reduce methane emissions. It is always we've done it, and we work together and very well together, and collaborative R&D is, I think, knowledge sharing, I think, is really important and will really help in the reduction of emissions. It's important for methane emissions, but is important for other research topics. And I'm sure you will hear the same conclusions tomorrow and the day after tomorrow. I think that's the work we've done with GERG to make a research roadmap, I think is an important one, because of it is really a possibility to make things more clear, look at the different elements, what we have to focus on, where we have to work on. We have, as I've shown you, we've been working with on the different elements of the value chain, on the different elements also of the methane emissions reduction management cycle. And I think it's an important work that we have done to identify where the gaps are and where the research priorities are. And that's based on this that we can develop now research projects to address all those important topics that we have been identifying. And the team of GERG has made a very good brochure, a summary brochure of this roadmap. And you see a little photograph of the cover of this brochure on the slide, and it will be publicly available after this conference. And I really invite you to look at it, to consult it. You will find the most important elements that from my speech also here. You will find it back in our brochure that the team of Robert, Alexandra, and all the secretariat have been producing. Thank you. This was my presentation of the roadmap. And now we're going to the next part, because presentation of the roadmap is one thing, but we've already been working, and it's also important to present you all important projects that have been done recently. And I think it's important to see all those work that has already been done, and I think I can be proud to present all those results here. So first off, I will give the floor to Christina.
Yes, thank you so much.
Thank you. Just sorry to interrupt, Christina, just before we go to your presentation, I wanted to remind everyone that we are not using the Teams chat today, but we are using the Slido tool to manage questions. So if you have questions from the following presentations, please go to Slido and use the code GERG60, and we will pick them up in the Q&A part. Thank you very much.
Okay. Perfect. So thank you so much, Alexandra, and good morning, everyone. I am Cristina Lopez, and I work in GERG in the RISE division, which is the research center. And today I'm here to introduce you this project, which is a technology benchmark for site-level methane emissions quantification. And this is a project which is split into two different phases. The first one is about the state of the art, and the second one will be introduced by Enagas later. So first of all, why do we need this project? And so, as you know, in the gas sector, methane emissions can come or not from unknown sources. In this case, they are named fugitive emissions. Once in the atmosphere, methane disperses rapidly, making it difficult to locate leaks and quantify volumes. So there are new challenges about measurement and estimation of methane emissions. Also ensuring the reliability of methane emissions is very important for gas operators. So up to now, the most used methodologies are named bottom-up, And so here you can see some photos about it. You can see a photo of the backing methodology, but also high flow sampling. And so there is a current interest for some research groups to develop new tools like this. But also you can have some quantification with camera algorithms. So what they all have in common, all these methodologies, is that you have to go to the source level. And that means that you have go to the equipment and look into the valve or node or whatever for the mission. But right now, there is an increasing interest for the so-called top-down methodologies that it's shared by multiple stakeholders, like, for example, technology providers or academic researchers. And this is because level 5 of what we call OGMP 2.0 states that there must need a reconciliation between both approaches. So what is a top-down approach? This will allow you to quantify methane emission at the site level. And so it is composed of a sensor, which will be based on infrared spectroscopy because it's selective to methane, so this is the best approach. But in any case, the sensor will give you a concentration in ppm or ppb. Then you will need some complementary measurements that wind data, for example, given by anemometers or other GPS data. And this sensor will be situated in a mobile platform. I will speak later what kind of platform we can find. And finally, you will also need an algorithm to convert these concentration measurements into a leak rate. So what I mean by leak rate is kilogram per hour or liter per hour, for example. So next, please. Yeah, however, there is still limited experience in the use of this tool. And that's why in this context, our project on methodologies for methane emission quantification was launched in the GERG Association. So there are 18 members implicated, and we pilot this phase at RISE. And we provided some 4 different documents that were peer-reviewed by some of our colleagues of TNO and LSEU. So thank you to all the members for your inputs and our interesting conversation. Next, please. And so, as I say, the main objective of this project was providing a state-of-the-art of different methodologies for methane emissions quantification and define the next steps for methodologies implementation, which is more phase 2. There are 4 different work packages. The first one is about satellite measurements. And so we provide a report on a peer review. But in any case, all this work was based on public communication and scientific articles, but also discussions with the stakeholders. So then work package 2 was about the top-down methodologies. And so as you can see, we would find other kind of platforms. They can be aerial, such as planes or drones, but also they can be land platform, such as this ground vehicle you can see here. Work package 3 was about methodologies for distribution network. And in this case, we try to look into the different campaigns that exist right now to see the different approaches used. And finally, work package 4 was about definition of next steps. And in that set, we organized 2 different workshops in which our different members can express their ideas or they need to organize phase 2. So next, please. Yeah. Work package 1 was about the state-of-the-art of satellites, and we could see that it's a promising, quickly evolving new top-down approach in which the concentration sensor is situated in this satellite. And so the objective of this state-of-the-art was understanding the different systems, their current limitation, but also to get a comprehensive overview of the different satellites that exist right now, and also understand their different technical characteristics. So here I put a picture that I'd like because I think there are 2 of the most promising satellites to detect methane emissions. On one hand, you have TRUPOMI, which will allow you to cover daily the site, so you will get daily data. But however, the resolution is quite poor. In that sense, it's not able to precisely locate the industrial site. However, there are other satellites, such as the one provided by GERG that will have a very good resolution and that able to situate the plum in your industrial site. But however, the frequency of the measurements it's higher, so you will have measurements maybe 1 time per week. And so the idea is that the different researchers are trying to complement these two approaches to have to do some research. I'm not going into the details because I think some of the members I put here, such as Cairo, GERG, which are data analytics providers, are speaking later in this afternoon. But anyway, next please, Alexandra. What we could conclude with the state of the art is that this approach is good to spot super emitters. And what I mean by super emitters is a site that it's emitting in tons per hour. But as the detection limit is about 100 kilograms per hour, it's not the best approach for midstream and downstream operators. I will say that it's rather for upstream operators in the United States, for example. But in any case, it is a really quickly evolving methodology. Next, please. Work package 2 was about top-down methodology. And in this case, we established a state-of-the-art evaluation of the current mobile platforms that we can find in the market, but not only, because we also looked for the different technologies under development in the laboratory scale. And so the idea was to help to select the most valuable methodologies to implement them in a test campaign. And what we could see in the state of the art, as you can see in the figures, is that, for example, land vehicles are situated downwind the plum at a distance of between 200 meters and 2 kilometers. And so they must be situated in the direction of the wind. But also you can get some lower detection limit with drones, for example, that will allow to represent 3D plums and to go into difficult access areas. We also looked for the most used quantification algorithms, which are Gaussian plume dispersion and mass balance. And also here we could see that there is another promising methodology, which is the dial technique. Here I put some of the different campaigns. We could see that there are not a lot. They were most carried in the United States. And so next, please, Alexandra. As a conclusion, we could see that there is a very broad panorama in terms of technique and TRL of typology of actors, but there is a lack of more comprehensive, reliable data and independent performance campaigns. In Europe, for example, they were not allowed. And above all, there is an important thing we saw is that the existing measurement campaigns showed limitation for accurate quantification for this technology. So this will need further research. Next, please. Work package 3 was about methodologies for distribution network, and I will go quickly through it because we have other colleagues that will speak about them later, I think. But in any case, the study focused on detection with mobile systems. As you can see here, for example, this is the Picaro device. And in this device, you will find on the top an anemometer to collect wind data. And then you will have the concentration sensor inside the car. And so you will have to plan a driving strategy to go through the city and to look for the most emitting parts. So there is also another kind of campaigns, which are mainly relying on the bottom-up measurements. And so we could see that the most reliable approach is based on the suction method. I put here an image. And they are based on direct flux measurements. And so next, please, Alexandra. As a conclusion, we could see that regarding mobile surveys, they are good to spot super emitters rapidly, but maybe with limited accuracy if we compare to the suction method, for example. But in any case, that there is a dominance of small numbers of large leak on methane emissions. And so this is an opportunity for a cost-effective way to reduce methane emissions. And so here I put also the different partners that could done a campaign with this kind of mobile measurements. And regarding direct survey, we could see that the existing measurement campaigns have shown the reliability of this suction method, though it could be time consuming because a measurement could last maybe 1 day or several hours. So also, yeah, thank you for to the different partners who could give me some information about the work. Next, please, Alexandra. And so I will finish my presentation with talking a little bit about Work Package 4, which was an organization of 2 different workshops to discuss about the next steps. And based on the findings of the previous work packages, the different members could express their need and propose detailed next steps. And so we all agree that there is a gap analysis about uncertainties and performance evaluation, and also that we need to find cost-effective methodologies. And so in this case, with this work, we saw that there is a need to test and quantify the concentration accuracy and uncertainties of such methodologies. And this project also produced a proposal to progress on top-down methodologies based on control release tests. And so I think this is the transition for Tanya's presentation, because with this proposal, we could launch phase 2. So next, please, Alexandra. Yeah, thank you so much. And Tanya, the floor is yours. And if you have any question, I will be glad to answer them in the link Alexandra gave you. Thank you.
So good morning. Can you hear me? I hope that you can hear me. So yes. My name is, thank you.
Yes, we can. So, hi, Tanya.
Hi, my name is Tanya. I work for Enagas, so thank you very much for inviting me to participate in this event. And so first of all, congratulations to GERG and the team for not only for the 60th anniversary, but also for organizing this fantastic event and also for putting all these friends around this virtual table. So as Cristina was introducing this part, so based on the conclusions of the phase 1, so the study of the state of the art, we decided to launch this technology benchmark for site level methane emissions quantification. So it was a first of its kind research project covering midstream assets, and with midstream I mean LNG regasification terminals, underground gas storages, compressor stations, regulating and metering stations, and valve nodes. So what we did, so we were simulating releases, so blind above ground control releases. So all of them were above ground and with flow rates similar to the ones that you can find in midstream assets. And we did this to analyze the accuracy of the most promising site level or top-down technologies that are doing quantification. So we split the project in 4 work packages. So the first one was on detailed definition and the preparation of the test. So the work package 2 was to carry out the test. The work package 3 was the analysis of the results, so the methane data that was obtained during the test. And now the work package 4 is the definition of the next steps for the phase 2B, which will be to carry out measurements in real sites in operation. So we also established an advisory board, so to validate the scope, the test program, and also to check the results. So it was a very good idea to have this advisory board because there were very valuable input from internationally recognized experts, from authorities, institutions, academia, industry, and civil society. So there are experts that are deeply involved in the methane emissions topic around the globe. So next slide, please. So who is behind of this project? So there are 15 partners. So this is a consortium of mainly gas companies operating in the midstream, and also some national gas associations. So next slide. So we started choosing a location. So now I will go through the forward packages to give you some additional information. So we started choosing the locations. So we found an hibernated compressor station that was located in Spain. So this means that there was no gas inside the station, so only the gas that we use for the control releases. It was also isolated, so there was no other sources of methane emissions near the installation. It was a flat field with rows inside and outside the asset, so it was easy for those that have to drive not only inside but also around the asset. And in this area, normally there's no strong winds. So next slide. So once we have the location, so we selected the 9 most promising site level or top-down technologies. Also the consortium, within the consortium, we decided to test 3 bottom-up technologies. We organized 1 week of this blind test with control releases. So this was done the first week of October. So we were testing the accuracy of the different technologies, and as I said, so to simulate the emissions that you can find in a midstream asset. So we just simulated 17 different emission rates from 0.01 kilograms hour to test the detection limit of each technology, and also at different heights and with different outlets to simulate, for example, vents or the diffused emissions. And then also the independent analysis to assess the accuracy and the repeatability of the test. The next slide. So how it was organized. So we decided to have external support. So for the test organization, so this was done between ENAGAS and Bureau Veritas Emission Services. So we selected Bureau Veritas as they had experience a lot of experience in the methane emissions topic, but also with other European projects similar with other hydrocarbons. Then the test program, so this was prepared between ENAGAS and the LSE. So the LSE is the Public Research Laboratory in France. So the other partners of the consortium, so they were not aware of the test program. Also, of course, the technology providers were also not aware. So then the field coordination was managed by Bureau Veritas, and now the independent analysis of the results. So this is done by the LSE. So next slide. Okay. So the flow rates that we selected, so as I said, so they were between 0.01 kilograms hour till 50 kilograms hour. So the releases were randomized just to avoid that the technology providers were guessing what the next release was. So we also have this at different heights to represent fugitive and vents. And so in the left part, so you can see an aerial photo of the installation. So there were 2 areas where there were emissions. So the area A, when there was only the node 1, and the area 2 where there were nodes 2, 3, 4, and 5. So in the right part of this slide, so you can see the control releases equipment that we use to simulate the releases. So if we go to the next slide. So there was only 1 test where there were emissions in both areas. If not, so we were informing the technology providers whether there were emissions in area A or area B. And then when it was in area B, so we were not informing whether it was 1, 2, or the 4 nodes emitting at the same time. So some of the technology providers could also provide emissions per node, and other technology providers could provide only 1 number for the 4 nodes, or in case that all of them were emitting. So in the right part of the slide, so you can see the vent stack. So it was where the node 1 was located. So it was 28 meters height. And the type of exit that we selected was an open end, just to simulate vents that you can find, for example, in a compressor station or in an underground gas storage or in an LNG regasification terminal. So next slide. So in the next, so you can see here the node 2 that was a 9 meters height. It was also an open end line to simulate vents. So next slide. So this is the node 3 that was 4 meters high. You can see it there in the middle of both structures. So it was the ring shaped to simulate diffuse emissions. Next slide. So you can see here the node 4 in the middle of this structure. So that was a linear equipment to simulate emissions. It was 3 meters long. And so there were holes along this small pipe just to simulate diffuse emissions. And the next slide, so this was also 1.5 meters, and it was an open end, and it was to simulate fugitive emissions. So next slide. So on the technologies that were tested, so we selected, as I said, so 9 top-down or site-level technologies and 3 bottom-up or source-level technologies. So you can see in the left part, so one of the pictures where with all the technology providers and some of the technologies that were tested. So now I will give you some additional details on each of the technologies. So if we go to the next slide, so ABB decided to participate with 2 technologies, the hover guard and the mobile guard. So both technologies have the same analyzer. So it was an off-axis integrated cavity output spectroscopy technology. So in the case of the hover guard, that was mounted in a drone, and in the case of the mobile guard, it was on a car. So next slide. So we also tested the technology of Ironman. So there were 3 technologies installed on a drone. So it was the non-dispersed infrared, the metal oxidized semiconductor, and the laser spectroscopy. Also the tracer gas of the Dennis Gas Center, so which was a cavity ring absorption spectroscopy for measurement. So the tracer gas that was used was acetylene. So next slide. Also the technology of CCOPS, which was mounted on a drone, with a turnable diode laser absorption spectrometer sensor. So it's an infrared device. And then the dial of the MPL, which is the LIDAR dial sensor, which is mounted on a truck. Next slide. Also the charm participated, so it's also the LIDAR dial, which is mounted on an helicopter. And so we tested also some fixed sensors. So Mirico participated with the Orion Methane. So this is the laser dispersion spectroscopy for concentration measurement, and they also installed 10 retroflectors along the installation. So just to return the laser beams to the detector for the quantification. So next slide. So here you can see the Sensia devices. So they participated with 2 cameras. So it was the Caroline, which is an uncooled long wave infrared detector. So it's an optical gas imaging analyzer. And they also participated with their Mileva, which is a cool medium wave infrared detector. And then on the bottom up or source level devices, so there was the FLIR camera. So with the new quantifier, the QL320, this is a handheld device. So it's an optical gas imaging, and so which is frequently used by the industry. So next slide. Also, OPGAL participated with the handheld optical gas imaging, so the IC Gas 2.0. This equipment is also very frequently used by the oil and gas industry. And then, so we tested the high flow sampler prototype that has been developed by RISE. This is a pneumatic venturi prototype. So they are using compressed air to generate vacuum and to suction the methane that was in the different nodes. So next slide. So this is just to show you an overview of how the texts were organized. So each of them had a duration of 2 hours. And so at the end, so the weather was very fantastic. There were only during one of the experiments that were limitations because there was no wind, and that was a limitation for some of the technology providers. But for the rest, almost for almost all of them, so most of the technology providers could provide data. So next slide. So we are at the moment with the work package 3 of this project, which is the analysis of the results. So this is done, as I said, by the LSE. So they are preparing an independent report. So they are doing an analysis of the data. So they are looking to the number of releases with valid data that were provided by technology providers, to the mean, calculating the mean relative error, looking to the threshold limit. So as I said, so some of the emissions were just around 0.01 kilograms hour. So therefore, it was important to check whether these technology providers could not only detect but also quantify these small emissions. Also they are doing analysis of the wind speed limitations of the technologies and other limitations, as for example the height or the geometry of the installation. And then they are also doing the analysis of estimates per node. So in the case that there was multiple node releases, so some of the technology providers could provide data per node. Others, as I said, so could provide only one value. But so the LSE is doing at the moment this analysis. So this report that will be ready now before the end of December, so it will be only for partners, and so it will be shared with key stakeholders, as for example, the European Commission and the United Nations Environment. But the idea is to have a peer review article in the first quarter next year, that this will be publicly available. So next slide. So and this is for the work package 4, so which we will be starting now in December to discuss. So this is the definition of the next steps for the phase 2B. So the idea is so we are still discussing among the partners, but the idea could be to launch in the Q1 next year this phase 2B. So we have identified that further work is needed to see how these technologies can be applied to reconcile the bottom-up or sort level that we are frequently using for the quantification of our emissions. And so therefore, the idea is that based on the findings of the study of the art and also the conclusions and the results of this second phase, so to select 3 or 4 technologies to go to an installation that is in operation, to go with bottom-up technologies and with some top-down or site-level technologies, and to work on the reconciliation of the data with external support. So this is key for the industry. So now in the forthcoming legislation, so we think that there will be some obligations for the industry to work on this reconciliation, and also those companies that have already joined on voluntary basis or GMP 2.0 have to work in this reconciliation during the next years. So therefore, we think that this second phase will be key for to continue working on this. And the idea is to go to at least one LNG regasification terminal, one underground gas storage, one compressor station, one regulating and metering station, and one valve node. And so I think that this is all that I had in my presentation. So in case you have any questions, so happy to answer. Thank you very much.
Thank you very much, Tanya, for your intervention. Perhaps we are looking for the moment at Slido where you can ask your questions. And there are for the moment some questions from Mr. Robert Ziegler. Mr. Ziegler, I would invite you to ask your question directly.
Right.
Don't hesitate to unmute yourself and, and ask your question.
Just doing that, yes. Yeah, I think there's two issues I have with the phase one of the project. I think that the classification that everybody is using, unfortunately, in this methane emission world of bottoms up and top down is really inadequate, because that lumps in remote sensing technologies with the top-down method, where most top-down methods really are just a mobile platform that aspires the air and measures at that point where that mobile platform is either on the ground or in the air. Whereas real remote sensing profiles the methane column to the ground. And that is the big difference. And I think this is something that we should introduce as a category, basically called remote sensing. And there was one thing. And the second thing was that on the satellites that are listed, obviously the Franco-German DLR CNRS Merlin satellite is missing. And that's the first satellite that has active sensing technology. So this could be a real breakthrough in the methane detection resolution and accuracy. And so I think that we should definitely keep an eye on that as well. That's it.
Yes, so I will answer your question because I was doing it by the platform, but I'm not really used to use this platform. For the first one, indeed, I agree with you. Like there is, well, there is, I will say, like a discussion or a debate between bottom-up definition and top-down definition. And I wanted to say, well, I didn't have time to go further into details, so that's why I keep the definition like this, like based on what we can find in bibliography. But yes, this is maybe something we need here in the GERG group to think about it and maybe to propose this other classification. So yeah, just to say that I agree with you, but I presented it like this based on bibliography work. So regarding satellites, yeah, we could find this DLR on Merlin mission, and it is part of our benchmark, and it is in our document. But here also in the presentation, I couldn't put all the different satellites because there are like many. But I just want to say that indeed this will be like the first active mission, but it's rather a demonstration, and its aim won't be to spot industrial sites. It is rather to cover all the globe and not to spot really industrial sites. That's why I didn't focus on it in this presentation, because for me, like right now, the most suitable for industrial monitoring is GHGSat and other ones with higher resolution. So indeed, we have to, of course, to take an eye on it. But for now, it's more like research to test the LiDAR methodology in the space. And I think it won't be in the short time able to spot really in industrial sites. So I don't know if I answered your questions.
Yes, no, you absolutely did. I will talk in my presentation a little bit about where the industry should look with the measurements. So I have my views on that. So we'll talk about that maybe later when I give my presentation.
Okay, so perfect. Yeah, it will complement it. So thank you for your questions.
Sure.
Thank you. I think we can go now to the next presentation. Charlotte?
Yes, so if you like, I can do the presentation. I thought there's just a coffee break before, but yeah, I can also do the presentation right now. Okay, so yeah, also welcome from my side. And today I want to introduce the GERG project MEME DSO. So next slide, please. So the MEME project was a project that we began already, some years ago in 2014, and MEME means Methane Emission Estimation Method. It was a two-phase project. So the first phase started in October 2014 and lasted to October 2015, and the second phase started in 2016 and ran until 2018. And for me, this was a very special project because it was my first project when I started working. And it was very great to work with so many partners from different countries and to learn about their mentalities and of course to see how they handled the issue of methane emission determination. And of course, this was also the objective of the project because we wanted to evaluate the methods currently used for estimating methane emissions in the gas distribution grid. And we wanted to identify best practices so that we could pick up the best pieces of each method of each country and to develop one method that could be applied across Europe for methane emission estimation. Next slide, please. What we found out during this project, or what we created, was a method that addresses all the relevant sources and types of emissions in the gas distribution grid. And it is as accurate as possible, but with a reasonable effort. So we always said during the project, we can do methane estimation very detailed and very accurate, but maybe then it's not possible for some countries to apply the method. And that's why we always wanted to find a good medium between accuracy and also between effort, so that the method could be applied European-wide. That's why we also introduced different reporting levels. So with the MIME method, it is possible to do a very detailed emission reporting, comparably with OGMP level 3, 4, or 5. But it is also possible to do a rather simplified methane emission estimation, comparable with OGMP level 1 and 2. For these different levels, we gave different input data in our report and also some simplifications that a country can do when data are not available. In total, the MIME method contributes to a more consistent methane emission estimation within Europe. But what we also found out was that there are some input data missing in the countries. So in particular, measurements. Of course, this is the current discussion, and it was also clear at that time that in many countries, measurement data are missing at the moment. So it's, we know how to estimate emissions, but the relevant input data are missing at the moment. And that's why several national follow-up activities were necessary, and that these activities were already suggested in the MIME project, and some of the campaigns started right afterwards, for instance, in the Netherlands and also in Germany. And I also want to introduce the German campaign right after. One important aspect is also that the MIME method was developed further, was used by Marcogas within standardization activities from the European institution CEN, and this standardization activities are currently running, and we will see when they will be finished. Next slide, please. Now I want to introduce one of the follow-up activities of the MIME project, and this is the German campaign, the German DBGW project MEDSO. And this was a campaign especially for the German gas distribution grid that uses the MIME method to estimate methane emissions. But the most important thing of the campaign is to generate current national emission factors by conducting measurements in the German gas distribution grid. And Meanwhile, we finished our measurements, and we did about 120 measurements on underground pipelines and about 110 measurements on gas pressure regulating and meter stations. Currently, we are evaluating all the measurement data, and the report is produced and will be published in the Q1 of 2022. Yeah. And this was already everything about my presentation. So if you have questions, then yeah, please go to Slido and I am happy to answer the questions. Thank you.
For the moment, we received and Charlotte, I see a hand being raised. Bert Wickering?
Yes, I have a question. The report for the situation in Germany, will that be public available for other countries as well?
Yes, it will be publicly available, of course, in German language, but a summary will also be produced in English.
Thank you.
Okay, no questions via Slido. So, Charlotte, you were right. I was really wanted to hear your intervention, and you were right about the coffee break. So I completely forgot the coffee break. So, Werner, you have a question?
Yes, no, Charlotte, can you say something to the next step in the DBGW under this area? We plan for the next 2-3 years, the next step in this project. Is it possible? Can you give some set into this one?
So currently it's not fixed what are the next steps. It's still in discussion, but it looks like that the measurement activities should be continued. So what we found out was that the measurements we did were very valuable and were important, but yeah, we have to measure some more things. And yeah, since we now have the requirements from OGMP that we should measure with one bottom up and one top down procedure, yeah, we would just continue with another measurement procedure after the project, I guess. But yeah, we will just know this by the beginning of 2022.
Thanks.
Kees, I'm going to give you the floor.
Okay, thank you. Can I start with the first slide, please? Thank you. Thank you for having me from rainy Netherlands, but okay. I will tell you something about a recent project we did for GERG. Can you give me the next slide? Yes, it is about the report of quantifying the leakage from underground pipelines. I have only a few minutes, but so I will keep it short and concentrate on the main message and the lessons learned. It is about the validation of the suction sampling methods and the challenge of measuring the emission in the gas distribution pipelines is to develop a traceable method for quantifying the leakages. And of course, we use this, as I said, the suction sampling method. And in order to inform you about that method and why we're doing, we made a small short video which I would like to show you, such that we are all informed about the method and its requirements. So, Alexandra, please, can you start the video?
Yes, Kees, let me just, sorry, I'm going to have to restart the sharing process to make sure the sound is included. Just find that.
Yes.
And that should work in a second.
the greenhouse gas methane is the most important component in natural gas. Leaks from underground pipelines are one of the sources of methane emission. Quantifying those underground leaks is very necessary for developing sensible methane emission mitigating policies. But only a representative fraction of the detected leaks are quantified, as quantification is time-consuming and costly, and repair is often urgent. Suction sampling by Kiwa has been identified as an effective method for leak rate quantification. This is how suction sampling works. The components required for the suction sampling are a gas chromatograph, sampling bag, methane monitor, airflow meter, suction pump, underpressure gauge, suction rods, and manifold plus flexible tubes and valves. 1. Localize the leak as accurately as possible to start preparing. 2. Carefully hammer the suction rods into the soil to a depth of 50 centimeters. To every suction rod, a flexible tube is connected. 3. Connect the flexible hoses of the suction tubes to the header in which the gas samples will be collected. 4. Connect the accumulating hose to the suction pump with inlet filter. 5. Connect the pressure gauge to monitor the underpressure. 6. And connect the pump to a blow-off pipe. Make sure to place the blow-off pipe away from the possible sources of ignition. 7. Pump and check during 5 minutes that no water collects in the lines between the suction rods and the pump, or in the pump input filter. 8. If all remains dry, then connect a methane monitor to a T-joint downstream of the flow meter. 9. Start the pump. Check all connections for suction of external air. Check if data logging is operational and mark the start time in the report. 10. Check regularly if there is still methane sucked from the outermost pipes. If not, move the suction rod nearer to the leak. 11. Mark the flow and concentration every 15 minutes and wait till you have 3 consecutive readings identical within 5%. This typically takes 4 to 6 hours. 12. Finally, note the reading of the airflow meter and the methane monitor. Fill the sample bag. Analyze the content of the sample bag with the gas chromatograph and calculate and note the leak rate and all other relevant situational data. All the data need to be carefully registered and analyzed. Only 1 out of 1,000 leaks are quantified, so each measurement is very relevant. Quantification of methane emission is important in order to find the best strategy for emission mitigation and reduce climate change.
Okay, thank you for showing me the video. As you see, it is a relatively simple method, but it takes about a day to perform. We in the project we just try to validate the method by using a known leak on our premises, a couple of leaks, and to check the accuracy of the method. You see at the top photo an area photo of the leak site. It's the small grass area near the buildings. And in that area we buried a couple of leaks of somewhat different sizes and different sand on top of it. And the leaks are the normal leaks, more or less the average leak size we encounter in the practice in the Netherlands, and they are mostly kind of pinhole leaks, as you see, and well, you can barely see it in the photo at the bottom of the sheet, but that's the type of leaks we are talking about normally. It's about 1/10 of a cubic meter per hour. But the distribution of the leaks is varies. The leak sizes varies enormously. Yes, please the next slide. If you analyze the method in some detail, you see you have a number of sources of uncertainty in your measurement. For the validation, we need to inject a known amount of gas, and that we can do with an accuracy of about 1%. You need to measure the suction flow itself. That can be done by also an accuracy of 1% if you use mass flow controller as a sensor. And of course, you need to measure the CO2 concentration, and with the gas chromatograph, you can also reach an accuracy of an uncertainty of 1%. A major issue is how complete is your suction. Do you really capture all the gas which is emitted in the soil? And as you see in the graph below it, starting the measurement, you suck an excess of gas out of the soil, and only after some time you reach an equilibrium between the leakage rate, which injects the gas in the soil, and the suction, which removes the gas. And it is in practice relatively difficult to see whether you reach an equilibrium, because there's also some noise, of course, on the measurements, and generally you will stop the measurements a little bit before you reach the absolute equilibrium. So there is a tendency to overestimate the amount of leakage. But the error is, well, more important, more significant than the other 2 or 3 errors. It is about 10%. So, and that was also a lesson in our project, that overestimation can occur, and it was mainly due to the repeated experiments in which we had different leaks and different measurements after each other, and you really have to wait quite a long time to remove all the gas, all the old gas of the previous leak out of the soil. So the way to prevent this error a little bit, and it's also mentioned in the video, is to place the suction rods at a larger distance from the leak first, and then gradually decrease the size on which you suck the gas out of the soil. But that's one of the lessons learned during our measurement project. Next slide, please. What we also did was looking at the measurements which were available in the Netherlands during 2 old campaigns 15 years ago. We measured in total about 67 leaks, and for various materials. And if you plot those leaking rates in the graph, as you see, you get an overview of how much variation there is in leak rates for different materials. I only took the low pressure measurements, and how much the variation is over the different materials, and how much variation there is between the leak sizes. And you see the black lines give the average leak size for each material, and the blue bars give the maximum and the minimum rates which were detected. And for instance, you see for the gray cast iron bar, for which we have quite a few measurements, because that was the purpose of one of those campaigns. You see a complete range between 450 and almost 0 leakage, with an average of about 100 liters per hour. And that's a pattern you see also for the other materials, sometimes a little bit less clear because you have only very few measurements. But you see that there is about a variation about just as large as the average value. And that means that you need 10 or more measurements in order to have an accurate idea of the average leak size. So that's also a point of uncertainty if you try to extrapolate these measurements to the total population of leaks. So that's the other lesson learned. And what we also see is that we did those 2 campaigns, but it is very hard to retrieve the information about it completely again. It is more or less a kind of forensic research in old documentation. So it is very important to do those measurements on a regular basis and to log down and to maintain the results and very carefully in a special database. So that's the other lesson we learned from it. Can you give me the next slide? So as a summary, what the current status is, I think that the protocol hardware experience is available to do those suction sampling measurements. There is a limited data set available for which we learn some lessons. The uncertainty, you need a lot of measurements in order to get a reasonable idea of the size of the average leak. So that's at this point in time the main source of uncertainty. And yeah, I would also advise to do more field measurements. That's always do more. It's always an advice, but in this type. This moment, I think, especially appropriate. And please look careful at your documentation of those measurements, because they are very, they need to be kept for a very long time, because they are reference data for the next couple of decennia. So that's about what I would like to say. Thank you.
Thank you, Keith. Was very interesting little movie to explain and very explanative of the work that you're doing. We have the next presentation. It's Adam, detection of measurement of the emission of natural gas from the gas transmission system. Adam, the floor is yours.
Good morning. Can you hear me well?
Yes, sure.
Okay, thank you. Okay, I just want to make a brief presentation about the project launched jointly by 6 transmission system operators, NAGAS, Fluxys, Gasunie Gas Systems, NAM, and GERG Gas. And it was called detection, as you said, and measurement of emission of natural gas in transmission system. Sorry, I forgot to introduce myself. My name is Adam Szybył. I'm a specialist in R&D division at Gas System. And the Gas System was the leader of this project. And I have a pleasure to be the part of it. And the objective of the project was to investigate and identify the most useful devices for detecting and quantifying methane emissions from infrastructure components typical for TSO, using so-called bottom-up approach. The project has 4 phases, and in phase 1, a survey of commercial unavailable leak detection technologies was conducted, and the test program was designed, and after analysis we got 5 methane detection devices, and 2 of them was also able to I didn't see my slides, and 2 of
just put them back again. So
no problem.
Sure.
I can go on without them. And 2 of them were also able to measure and quantify the leak, I would say indirectly, but I will talk about it later. In phase 2, selected technologies and equipment for testing were acquired. Then testing was conducted by both under controlled, so laboratory, and uncontrolled, so in field conditions. And I think that that is a good example of the project and the collaboration in hard times, because we started the field tests in March 2020, and for sure you can remember the panic back then, and but somehow we did it, and we was able to close the project. So in third phase, okay, this slide is okay, it will be in a few seconds. In third phase, summarization and evaluation of the testing methodology was for possible incorporation in European standard was made. Of course, recommendations based on the test results and project team experience. And there is also evaluation of the possibility of using multiple technologies to characterize natural gas emissions. And of course, the final phase was the incorporation of the comments from project members. So those are parameters that were evaluated. And one of them was ease of use, because I'm sure we all need and all want to find a method that is maybe not so its accuracy is good and it's easy for use and so on, as an alternative to bagging, which is very time consuming and it's making our lives quite difficult because of numbers of measurements we have to do right now, and we will have to do. So we evaluated those parameters. Cost of acquisition, of course, speed of operation, errors, accuracy, and the most interesting was the last two instruments, and one of them was the principal was ultrasound acoustic gas imaging, and the second one was optical gas imaging, infrared. So that's a bit indirect method because it requires post-processing. So what we found, next slide please, if you can. Oh, thank you. What we found that there is at the market right now, there are unavailable new technology, new devices that are promising, but they are still developing. The accuracy isn't quite there right now, but with the development of software, because the measurements requires post-processing in both cases. So it depends heavily on software and on the database to feed the model, and the bigger database, both quantity and quality, it will be getting better for sure. And the question is when it will achieve this satisfactory accuracy. And the other main conclusions are, since the use of more than two instruments seems not to be feasible economically, and a combination of measurements, instruments, and other detection unit might be a good option to reduce constraints from the single instrument, because every single instrument has some constraints especially when we talk about the measurement, because it isn't such a problem in detection. The combination of two instruments implies that either one instrument will be the main one and the other will be supporting one, and both instruments need to be used at the same time. The combination of expensive technologies that also require more than one surveyor will become less attractive, and that's quite obvious. And the main factors that are influencing company decisions for LDAR are the company's needs and objectives for LDAR, the frequency, and other cost-effective factors. So, of course, the result in the database is quite big, and we didn't have time to talk about all of the results. But next slide, please. Yes, and here we have a test bench, how the test bench looked, and example results from the report. We tested few component types like valves, flange, connector, and open-ended lines. And I think that's it. If you have any other questions, maybe about the details and results, you can ask. I will be happy to answer them.
Thank you very much, Adam, for your presentation. I don't see any questions for the moment for you. Also, in order to have a little bit respect of the time, I'm going to give the floor now to Werner. Werner, you're going to give us the perspective of the German network operators. I think you have a very interesting things to tell us today. Werner, the floor is yours.
Yes, hello, I'm proud that I can speak again to you. I go out of my job for maybe 1.5 years, and from my activities today, I'm sitting in the German DVGW steering group for methane losses from the DVGW, and we control or do organize all the projects in Germany for methane emissions, from transmission area, from distribution, from devices, start and stop emissions, from gas installations. In the group, we are looking for all activities. We start a research project in this area, and we bring these results to the German government side and say what is the action situation in the gas distribution field. Can you have the next slide, please? And when next spot, next one. Next, okay. And here you see what is the current situation. We have nearly 6% of the methane emission is a TH, as the global warming emissions, came from methane. And if you look then to these areas, and 9% of the 6% is coming from the diffusion emission from oil and gas. And if you look then to the areas, transmission, distribution, you can see for nearly 45% of all emissions now is coming from the gas distribution area, and nearly 40% is coming from the transmission. So we say we must do something. We must reduce 45%, and in total, we discuss it with the German ministerium. for economic, we have nearly 5 million tons. That is nearly 0.6% of the total emissions in Germany will come from the gas industry. And that was a positive signal, but the answer from the government side was not everything is positive, but the answer from the government side in Germany, we must reduce 0.6%. It's not enough. It's nothing for us, but it's not enough for the government side. We must reduce with this 0.6% in the next time. Next slide, please. And next one, okay. That means that we changed from 1990 to 2070. We reduce in all time nearly 40% of the methane emission in the time. And what we have done, we do many things for leak detection and repair. We control and check every year or every 6 years in pipelines, repair in very short times. We started investment programs. We make a replacement for cast iron in Germany. I give you later on more information for this. And we started training and technical staff management. We have many actions for this one. And the result was that we can reduce the emissions from 1990 to today by nearly 40%. Next one. This is important to look what is the influence from the material side. We have nearly 380,000 kilometer main tubes and nearly 130,000 kilometer service lines in different material classes. And one important class was for the methane emission was the cast iron system, and was nearly 10,000 kilometer in Germany in the starting point 2000, and we reduced the cast iron system nearly to zero. And what we have done in that side, please, next point. You see, if you compare the situation from 1990 to today, in 1990 we have only 20% polyethylene pipes. Today we have in the grid really about 55% of polyethylene pipe. Why it's so important? Polyethylene pipe, as we see in the grid, that polyethylene pipe have a very low leakage rate, and so we have very low emissions in the atmosphere. But the discussion is running over, so we have looked today for the permeation gas. If you look in the UTMP document, one factor is the permeation gas. Now, from my point, we look a little bit for this one. We develop new material classes for this, more another pipelines for new installation that we can reduce this one too. And in general, it's very positive. The reaction in Germany to increase the polyethylene pipes and gas distribution. Next one. Here's the starting point. We started with the reduction of cast iron 1996, and it was not an action for methane emissions. It was only an action for safety. In this case, in 1996, we had big explosions. Why? We have many heavy traffic in the cities, and the cast iron were broken at that time. And so we started the project, and now we can see we have nearly no cast iron more in the nearly zero in the German gas distribution area. It was a really big success story from my understanding, and we increase the safety and reduce the methane emissions. Next one. Why we have done? You see the red line. The red line is the leakage rate, from cast iron system, and in general, we can say in this document, we reduce the cast irons, and in 2014, we can say today in 2017, we have a low emission leakage rate in all material groups. The question is not more to change material. The question is more to handling the leakage rate. We are very low leakage rate level in all materials. I think by PE we have now a leakage rate level by 0.02 leaks each kilometer in here. By steel, if you look to a new steel material, with PE coating, you are in the same range. If you look to older PE, steel pipes is a little bit higher. But in general, we have a low level from leakage rate in the German distribution grids. That's important in the discussion for the government side. And that is the results over the last years. And what we have started now is the third-party access volume stream. If you cut in Germany, if you cut the service line, if cutting a machine cuts the service line, the gas can go out. But in the year 22, we started installing each service line a gas stop. It means if a machine gets the service line, automatically we stop the gas stream, so we can reduce the methane emission too. Next one. That's different in the material class. You see in the middle PE and PE with active corrosion protection. And in general, we have very low levels. And in the middle, the cast iron system is nearly 0.363. In the old one, today we have no cast iron system more, nearly nothing, no cast iron system more in the fields. And so we see we have very low levels. And important is from the pressure side that only 80% of the grids are lower in the pressure than 1 bar. It's important for the calculation. Next one is for service lines. Next one is for service lines. You see the same little bit in the technique. You see in the service line. You have more external influence. For this one, we have today the gas stops integrated in the system, but in general we see in this area as the same level very low leakage rates, and that's important for the discussion with the government side. If you calculated this one, it's the next one. If you calculated next one, please. You see here the results. The substitution in the last year was nearly 10,000 kilometers in cast iron. The leak reduction at the time was nearly 3,500 leaks every year. If you calculate it with 150 liter each hour, and the lifetime of the leak is 0.5, you can say we can reduce every year the methane by 2.25 million cubic meter. And that's a direct reduction of the methane emission in Germany. We measure the 150 with the success methods. I developed this technology with Mr. van Heijden in a GERG project in the year 2000. It's not clear. It was a project with natural gas, in that time gas de France, and we developed this technology what we need today in all the field installations. It was a GERG project, and a very I think a very good project that we can come together. You see Ruhrgas at the time, GDF, Italgas, Natural Gas, and other companies. We had this one. We tested different methods, sheeting methods, this technology, pressure tops, the technologies, different technologies, and the success method was one of the best. Next one. What can we do? That is more important. We can discuss every time we must reduce the methane emission. With the new measurements, we can reduce it in calculation, the methane emission, not more. In practice, it means if you calculate it today with a higher level with a high volume stream, and in the new world, with a new measurement, we can reduce it. But in total, in the practice, we do not reduce the methane emission with this factor. And what we must understand, in which area we must something do that we can reduce really the methane emission. I will say today, not more methane emission. I will say more, that is a point for GERG, gas emissions. In the future, we have not more methane inside. We have more renewable gas. And for this one, I think we must change, on my understanding, we must change a little bit of discussion, gas losses in the gas infrastructure. That is important for the future, my understanding. And if you look in in the different classes, we have 3 classes of methane emissions. One is the volatile methane losses. It means small corrosion points. And second part is the operational losses that we can do. We can do something for this to reduce the pipe pressure if you make working if you do something in the pipe, and the pinhole is not really direct to reducing. And from my understanding is in the first group in the gas distribution we have nearly, I would say, 60% of the losses are laying in this group. And for this one, this is important. We see in the material class in Germany we have very, very low level of leakage rate. We do many things in the maintenance strategy that we find the right for the replacement program, that we change right pipes in the grid. That means with high leakage rates. And now we must. What can we do in the next step? That is, I think, that is in the discussion in Germany. We want to start for this one a project to calculate it, what we can do it if you make a new frequency for leak controls. Next one. Here on the left side, you see under 16 bars what we do. We have a different classes. It's the leakage rate lower than 0.1 and the pressure lower than 1 bar. We must control this pipeline every 6 years. In general, it means PE pipes. If the classes is the leakage rate by 0.5 and the pressure is 1, we must do every 4 years. Another one, you see, we have nearly every 2 years we must check the pipe. If you calculate it then to the yearly leakage rate, you see in the first class we have nearly 0.016 leaks each kilometer and year. Then you can go in this classes with every 6 years. In practice, you have 100 kilometers, you have 1 leak. In the old and in the steel pipes, I would say, in the years from 1950 to 1970, you are in the classes by 0.125. It means for 100 kilometers, 12 leaks. So if you want to do something, it's better to focus in this area. And the question is now what we can do. What is the influence if we change the inspection times? Or the inspection times have 2 influences. One is for safety. We think for the safety factors, everything okay in Germany, we have no problem. But if you add more the discussion for environmental aspects, then we discuss again this topic to change maybe the inspection time, or we find a new way that we control by 50% the inspection time with new technologies to find the big holes in the grids. And in the European documents, you can see that 5% of the leaks in the gas grid have nearly 50% of the methane emission losses. So the idea that we can look for this one, is it possible to change a little bit in the times, that we can reduce maybe the lifetime of leaks in the grids, and this in this case we can do it. We can reduce the methane emission. And in the next formula, you can see the direct influence. Leak frequency, this is one. I think that we say we are on the very low level. Leakage rate, that is a project from the DBGW. We are looking at this one, what is the middle volume stream, and important things is repair period, control period. Can we do something? And that is the discussion in the new project. We want to look at what is the effect. If you have, say, if the material in a good situation, we cannot only look in this case look more in the inspection time to reduce it. In this case, we reduce the lifetime of leaks in the grid. Next one. And for this one, I can make a small calculation. In the first area we see here, that is what is today In the first group is PE, and the second is steel. We checked the PE pipe every 6 years, steel pipes less than 1 year every 4 years. If you calculate it over the German grids, then you can say by steel 4 years means in the middle the lifetime of the leaks is 2 years. Then your repair time 0.5. That is means that in general you have a lifetime of 1 leak by 2.5 years today, and by PE by 3.5 years. And if you then calculate the gas losses for the total grid PE, we have 4.7 million cubic meters in the year, and by steel nearly 20 million. Now I changed the control time in the variant C. You see, I go from 6 years to 4 years, and that means that the lifetime is only 2.5, and the same we reduce by steel from 4 to 2, and that means that the lifetime is 1.5. And with this way, reducing the inspection time, so you can reduce then maybe in the first step the methane emission by 38%. That is the first calculation. We want to do it. We want to analyze in the DVGW project again. We want to make it a little more concrete, this area and this calculation way. Maybe after the process we can bring it in the DVGW standards. Next one is the last slide. Introduction and next one. And into the introduction, no, back. Yes, right. Introduction of increasing state-oriented statements, new technologies. If you want to change to control the pipes, is it not possible to do it only to walk over the pipe? You must find for this one, from my understanding, in control system. Maybe we go by car. It's not possible in Germany. Or we have another techniques to control to find the leakage in the field. Then we discuss the inspection and repair times, and for this one, in this arguments, we can reduce the methane emission. That's what we want to do in a new project. We want to calculate it and want to show is it a really good point to go this way. Last one. We on the way in Germany. In general, we say we have very low leakage rate in the gas grid, distribution grids. What we can do in the grids is only to go in the inspection times to reduce it, and that's the topic for the next 1 or 2 years. And in the calculation platform, that is what I see, we want to add the results from the DVGW project from the DBI, and then we have a new platform to reduce the gas emissions in the German gas grids. Yes.
Thank you very much, Werner. In the interest of time, I know there are some questions coming in with Slido, and thank you, and I encourage everyone to ask their questions via Slido. There was one for you, but I don't know if you can answer it on a very short time. It's will the question from Andy Duncan, will the methane network in Germany also be suitable for blended methane hydrogen or pure hydrogen in the future? I don't know if it's a short one or if you say yes, we will speak about hydrogen on Friday. So
yes, the short one is we have in the discussion from the distribution company, we discuss many projects, or we do many projects for the blending gas. We started now in the Avacon group by 20%. It's nearly the same as a high deploy project in UK. But in each case, we have pilot projects in the planning phase for 100% in distribution. If you look then to the political party, to the political side, in this case, we see in Germany they want to have more, only pure 100% hydrogen in the grids. It's more in the transmission, not only in the distribution. But that is a running process for the future. What is the right way for us for the future, blending or 100%. The political parties see more 100%. Yes?
Okay. There was also one for Kees. And I'm looking for the question because it was, I can't ask the asker because it was anonymous. Kees, I don't know if you're still there.
Yeah.
I'm reading you the question. How would you account for the uncertainty of the suction method when evaluating the measurement data to determine emission factors and their uncertainty?
Yes, the short answer is that the accuracy itself, the repeatability of the method is about 10%. And then you have to do your statistics about the number of measurements which are available. And that is also addressed, that question is addressed in the document that is being prepared by the working group of CEN about methane emission. I think Charlotte also referred to that. So, but essentially it is called the method of propagation of errors, and it is a more or less standard statistical method to calculate the uncertainty of your final answer, taking all the uncertainties of the intermediate steps into account.
Bernard, I see that you raise your hand.
Yeah, I have only one point for the GERG group. I think in the past we have in the GERG a PE data bank. Is it possible from GERG to thinking about maybe a gas leakage data bank, that we have all the information from each country to bring it together? That is from Kees, I think. In Holland, Netherlands, we measure nearly 45 points. In Germany, so before, we have 120 points with the success methods in Germany. Is it a GERG actions to bring all these points together, that we have one database for all these measurings, what we have done in Europe? I know Italy measuring with the same technologies, and why not? We can do it and can start a database so we can have only the same information. My question to GERG, to the president. The president.
May I interrupt you, Werner?
Yes.
Because I think IMEO is already doing this, isn't it?
Well,
IMEO.
I don't know.
Can anyone say something about IMEO in the OPNC program 2.0?
But this is OGMP is only a small groups from interdistribution from companies. But I think GERG is open for all that have done something. That is my idea. Only to bring it together. I think is that in general, at the end of the process, you have emissions factor for Europe for pipelines, for gas distribution pipelines. That is the end of the process. But I have no the information. It's very complicated to come to the information from each country. Countries. I tried for 1.5 years, but it's not too easy to come to this information. I think GERG is a good platform for this one to bring it together. We do many things in the methane emissions. Why not we can bring it together in a good platform with all the values? And that's my only idea, not more.
I see that Bert, you have raised your hand.
Yeah, I don't understand, because IMEO, I think, is already doing this. Investigating and making a platform for all the information that's available, the data, and that's worldwide. So maybe GERG can be also play a role in this, but to my understanding, it is IMEO who's doing this.
And how many measurements do we have from each country inside?
I think we're going to, I really have to interrupt this discussion. I'm really sorry because we are running already half an hour late. I'm really sorry. I think I have to intervene here. we're coming to the next part, which is a discussion, a panel discussion. I have 3 panelists here. For the questions, please please use the Slido. This will help the Secretariat and myself to look at the questions that are coming in during the presentations. Now I'm going to give the floor. We're going to look at all emerging methane emission quantification technologies, about reconciliation and validation. I have 3 speakers, 3 very interesting speakers. First of them, or it will in different order, and that doesn't matter. The order doesn't matter because they are all interesting. It's Christian Lelon, who is responsible for environmental solutions at Kairos, and over the past 2 years he has been particularly focused on their methane monitoring platform. His background is in investment research at Goldman Sachs and in natural resources at BHP, the world's largest mining company. Christian, the floor is yours.
Thank you very much for the introduction, Alexandra. If we can go to the next slide to just introduce Kairos. So we're a geospatial analytics firm based in Paris. We've been around for 5 years, and we've been working with the energy industry from day one, initially to look at the supply chain and using remote sensing technology. But we've been very focused on the environmental side in the last 2 years. So we don't operate satellites, we use satellite imagery, and we focus on the analysis. And this year has been very good for methane. If we go to the next slide. At COP in Glasgow, John Kerry made a number of interventions around methane. And in one particular discussion, he mentioned an article in the Washington Post about the detection of methane hotspots in Russia and how that was a big topic. This article refers to some analysis we had published and quoted sources in Russia that are reacting to this data and, you know, sometimes agreeing, sometimes deciding that they need to also invest in satellite imagery. So interesting that methane became a big topic at COP with the Global Methane Pledge and the launch of IMEO, which was mentioned in the previous panel. And on the European side, of course, very active. The European Commission has been really on top of methane. This is Kadri Simpson, and one of her tweets referring to, again, the detection of hotspots in the energy sector. So methane is very much top of mind, and satellite monitoring is one of the key tools we have to address it. If we go to the next slide. So a lot of the discussion so far has been on these hotspots. So these are the orange dots you see on the map. These are very large concentrations that we detect using European satellites, typically above 5 tons of methane an hour. So definitely very, very large, but there's unfortunately a lot of them. And so one of the points we have been making, including to European regulators, is that if the industry could ensure that all these very large sources or these super emitters could disappear, the impact on greenhouse gases would be in the order of 1 billion tons of CO2 equivalent. So I'm going to talk a little bit about how we measure methane emissions. If we go to the next slide. So we have developed 2 methods based on satellite imagery. The first method on the top is called a basin inversion. So this looks at average concentrations in a region, and the objective is to measure the total methane footprint of an oil and gas basin or of a coal basin. So we're going for being as comprehensive as possible. The second method on the bottom is detecting individual releases of methane, which can be vented emissions, or it can be fugitive if there's, for example, a big accident, or if there are a lot of sources tied together. So 2 different approaches using the same data. We're using images from a European satellite called Sentinel-5P, but applying different models. If we go to the next slide, I'll talk about how the basin inversion looks in practice. What it allows us to do is to follow the total footprint of a region starting in 2019. So in this example, we have data for Turkmenistan, which is one of the biggest emitters in the planet. And so we're able to follow over time the total footprint of oil and gas production in Turkmenistan, with separating the eastern half and the western half of the country, which are two separate production areas. And so we can see that, unfortunately, the trend is not downward. It seems to be relatively range bound at around 4.5 million tons of methane per year. So great tool. We can now see for the first time the total methane footprint of all the producers in a given basin. If we go to the next slide, it's worth highlighting that this is not just about gas. Coal is also a big source of methane emissions, and this same methodology works actually very well in the coal mining space. So this is an article that appeared in the Financial Times this summer, based on some work we did of a large coal mining basin in Australia that provides the steel industry in Europe with a big part of its coal. And we can see that this coal has some imported emissions of methane that are higher than was previously expected or reported. So again, measuring the full methane footprint of a region, whether it's oil and gas or coal, or sometimes both. If we go to the next slide, in terms of validating these measurements, one reference point is the International Energy Agency. What they do is they look at all the scientific literature, they look at the numbers from the IPCC, and they have their estimates of methane emissions per country. So that's the light blue bar. That's the IEA estimates. And the darker blue bar is our results based on satellite monitoring. And here we're expressing it in kilograms of methane per barrel of oil equivalent. So take all the methane that we see and divide it by the production of oil and natural gas. And so we find it very satisfying that our results are very much consistent with what the IEA was expecting to see. Sometimes we're a little bit lower, sometimes we're a little bit higher, but it's largely consistent with what scientists and international organizations expect the global energy sector to be emitting. If we go to the next slide and now talk about hotspots. So these are, again, individual releases of natural gas, and sometimes they are voluntary. This example on the top is pipeline maintenance in Russia. So you see the colors indicate the concentration of methane. That's what we get from the satellite. And the work we do is identifying these automatically and then doing the quantification. So the plume on the right, more intense, is 62 tons of methane per hour. The plume on the left, about 30 kilometers away, was rated at 19 tons an hour. And you can see the wind is blowing from the southwest. So this is all parallel and moving away from the path of the pipeline. Sometimes we have access to higher resolution images. So in this case, we have the separate satellite flying by at around the same time, and we can clearly see the cloud of methane coming out of that Blackwell station on the path of the pipeline. So this is something we're monitoring constantly, and we know, based on the research we've done, that these sources account for about 10% of total emissions in the energy sector. So it's the tail end. They're relatively less frequent, but because they're so big, they still account for a decent amount of total emissions. And so our argument here is this is a low-hanging fruit. If we could make sure that these are eliminated, that would be a very good outcome. If we go to the next slide, In terms of validation of these detections and quantifications, we have been working with Bloomberg for the better part of a year now. And the great thing with these partnership is that Bloomberg sends their journalists to investigate the hotspots that we see using satellite data. And they call the companies up and they get to the bottom of the story. So for us, it's been great because it creates awareness. It's not just the scientific community or governments, but now it's the financial community and companies that are becoming familiar with the topic of methane. But they also help us to validate by contacting the pipeline operator or contacting the oil and gas producer that was suspected of or likely to be associated with these methane detection, and then they get to the bottom of the story and confirm that yes, there was something going on, again, either voluntary as scheduled maintenance or involuntary like unscheduled maintenance or some sort of technical malfunction. In terms of the the bigger picture, if we go to the next slide, we know that the work ahead is going to be about integrating the different sources of data. So we work mostly with monitoring satellites, but there are also tasking satellites, which are a little bit different. There are aerial and ground sensors, and we know that in the end we're going to need that top-down view that I was just showing you now, and the bottom-up view, and make sure that they reconcile. So this is going to be one of the important work streams ahead of us, because every sensor brings its own value, and that's what I tried to show in this diagram. Satellites have the best frequency and range. They're looking all the time. They see the whole planet, but the ground sensors have the best resolution and they have the greatest sensitivity. So ideally, we want to combine them both. And in terms of the governance of this whole thing, if you go to the last slide, the IMEO is, I can't emphasize how important it is. It was officially launched a month ago. So it's going to its mission is to drive the science of monitoring methane, ensuring that we have one version of the numbers, taking as inputs the work that we do, the work that others are doing, and to then compare against the numbers reported by operators and give their opinion if those numbers are solid or not, and guiding them to follow OGMP 2.0 and work their way towards level 5, which is the highest standard for reporting emissions. So what we've done is we've collaborated with the International Energy Forum, so the IEF, to help companies and countries go towards that end goal by integrating measurements from satellites and other sources as soon as possible. So this is how satellite monitoring fits into the whole picture. It's about implementing the goals of OGMP 2.0 and sharing that with the Methane Observatory. So I'll leave it at that because I know time is short, and I'll hand it over to the next speaker. Thanks, Alexandra.
Next speaker is Lola Odunsi. She works for GEG SET as an international sales director. She's strategic advisor in the energy sector to independent national and multinational companies and regulators in developing optimized advanced technology solutions that accelerate their decarbonization plans. Lola has worked in geoscience, digital and sales roles with ION, Paradigm and Schlumberger. Lola, the floor is yours.
Thank you very much, and thank you for the introduction as well. And it's great to join you here from the UK. Today, over the next sort of 10 minutes or so, I'll talk you through the key aspects in terms of methane emission monitoring at facility level. So what I will do is probably just start off with the identification of these emissions. How do we identify these emissions? And then I'll just move on to the quantification of those. And then finally, in terms of the validation of those methane emissions that we detect at facility level. Can you still hear me okay?
Yes.
Okay, excellent. So to start off with, GHGSat sort of comes to mind when you talk about facility level measurements of methane emissions from space. So who are we really? Well, in 2016, GHGSat sort of pioneered the monitoring of methane from industrial facilities using satellites. So we built on decades of experience by space agencies in monitoring greenhouse gases, you know, at a regional and global scale to inform sort of climate models. So based on all of this information, and with the launch of our demo satellite in 2016, we leveraged on that, on the lessons learned, and incorporated them into our next 2 satellites. And this resulted in about 10 times the improvement in performance. So the plan going forward is to kind of ramp up the satellites. We've got 3 planned for next year. We've got 5 planned for 2023. And to add to Christina's comment where she made earlier on, the plan is to get to a point where we can actually have those daily readings with this increased constellation. In addition to that as well, we do have the aircraft variant also being built to sort of complement the satellite measurements. One thing I'd also like to point out is, I know we've been talking about IMEO, Bernice mentioned it as well, but just to also say that, you know, the Canadian government will be contributing to the IMEO using GHGSat's data. So IMEO will integrate our data, our information based on the emissions that we've gathered around the world, and include this as well in the national inventories and, you know, and the members of the OGMP information as well for the trends and for insights, etc. So I think that kind of answers some of the questions that was being bounced back and forth during the conversation as well, is the fact that, you know, there are incentives already in place to kind of address the build-up of data, so to speak. So next slide, please. Okay, so let's start with identification. So here I show an example on the image that you see. It was captured by one of GHGSat's satellites from an oil and gas facility. This was in Central Asia. So here we have a mix of different plumes, and only 2 of those could have actually been detected by public satellites. So say, for example, if you look at the Sentinel-2, which can also actually look down to facility level because of the high resolution it has, but it only sees a very big emission. So say, for example, the one in the middle and maybe the second one from the top right, everything else will be missed. So you need that low detection threshold for the full identification. And with our low detection threshold capabilities of about 100 kilograms per hour, we were able to identify 8 plumes in the same satellite pass in one field of view. So if I kind of just draw your attention a little bit now to the green panel, so what we're seeing is also an increase in the number of emissions detected. It's an upward trend as industries sort of ramp up production, etc. And what does this imply? So this implies the increased need for emission monitoring and an unequivocal attribution and identification right down to site level. I know Christina mentioned also as well in her presentation, we've also talked a little bit about the OGMP 2.0 framework. So although I do believe that this is a dynamic working document, this sort of confirms the level 5 being attained by using aircraft and using satellite measurements down to facility level, which is pretty much right, you know, right up GHGSat street, so to speak. So next slide, please. Okay, so I've talked about identification, so I'll move on to quantification. So we're constantly reviewing our measurements and performance and how the instruments are working, and they're credible, they're quantifiable, etc. Now, here's an example of a controlled release. I know we've talked about that as well during the course of this session. This was a blind test that was carried out with Total. Now, what happened here was Total did not specify where the emission will be. They didn't specify the volume of emissions, etc. But we were able to actually identify where the emission was coming from. We're able to identify the volume, the size, as well as the emission rate. So again, in terms of quantification and verifying that those numbers that we're producing are accurate, in here, for example, we estimated 250 kilograms per hour, and Total released on ground 234 kilograms per hour. So, I mean, this test was carried out I think about a month into the launch of one of our satellites, and it kind of just showed the credibility in terms of the derived measurements made with the new launches as well. So next slide, please. So to further sort of buttress on the point I was making earlier on in terms of QCs for quantification, I mean, the Total Energies was one example, but we have also shown so many other controlled releases as well that have been performed. Some of them were blind, some of them weren't. What we focus on as well in terms of doing those quantifications and the controlled releases, we will check to account for things like the terrain, the weather, cloud conditions, etc. And then we just completed as well a campaign recently, and this was with, dozens of additional, blind results. And so you will see some more examples in this chart that I show very soon. But then the takeaway is that our derived estimates are in agreement with the one-to-one released rates that, shown by the green line. Obviously, we do have some exception of outliers. And how are we addressing these outliers? Well, the key is that this is where the benefit of the repeated measurements come into play, and why we're increasing our constellation of satellites for these, for the repeatability as well. Next slide, please. So I've tried to talk through very quickly in 10 minutes, but here's the last slide I've got. So I've talked about identification, I've talked about quantification, and now I talk about the validation. So basically, when you're looking at satellites for measuring emissions, the one thing to note is that one size doesn't fit all. So the satellites have different capabilities, and they're all different. They can't all do everything, so to speak. So in other words, they are complementary. So you need to understand, your needs, because your needs will dictate the type of satellite or the combination of satellites that you actually need. So say, for example, in understanding regional and global distribution of methane, then you can use a Sentinel-5P, Tropomi. These satellites are built by operators that, they are operated by governments and, legislations, etc. They could potentially be quite big and costly, but then they will provide you those regional and global overview at about, say, 7-kilometer resolution. Now, if you want to see sort of the world's largest emissions, then you can probably start looking at Sentinel-2, as it shows really big leaks as well. But then the issue with that is, could it be operationally significant? Now, if you then want to get to the level where you're kind of comparing with your peers to see how you're doing relative to your neighboring assets down at facility level, then this is the reason for our satellites, GHG satellites. But then if your goal is to, for example, to find those leaks, to go through the leak detection and repair, as well as for reporting, then high resolution, low detection threshold, you cannot compromise on. And again, this is some of the capabilities that we do have. But finally, what I would just like to do is kind of just wrap up with this graph on the blue panel that you see on here. So to that graph, it shows the relationship between the emission of the plumes detected versus the rate in a 3-month period from January to March. But what you will notice basically is most of the detection within that 3-month window, they are smaller plumes. Now, for example, for the Sentinel 5Ps, Tropomi, etc., they would only see the emissions, say, for example, to the right of number 5 on that graph. So this is not to say that they are not important. In actual fact, they are extremely important, and they're very, very significant indeed, and would make a very big difference if they were to be eliminated, right? And they're usually, but the thing is, they're usually quite catastrophic in the sense that most of the time you would already know about it. But operationally, you want to get down to about 1 to the 1.5 tons per hour, because you will see, as you can see on this slide, you're seeing much bigger quantities of them. The frequencies of them are more in this case. And then obviously, once you start to look at that as well, then you can start to make those immediate effects as well. And those could also make very, very big differences. So basically, as mentioned in the beginning of my presentation, we have been working very closely as well with public satellites for years. But it's good to bear in mind that although, you know, when we're talking about validation, it's very much needed to ensure that the public satellite information as well doesn't provide you false positives. So it has to be all incorporating when you're looking at emissions using satellites. So in terms of my summary, what is the key summary? I think David Salisbury mentioned it in his introduction as well, is that this is not competition, but more about how we can work together in a very cost-effective way as well, in a tiered option. So going down from satellites down to ground instruments, etc. I believe this is what Kristen also mentioned as well previously, is having that tiered cost-effective approach. And in detecting small and large emissions, collaboration is very key. Cooperation is very key. And working together is very, very important. And this is kind of the ethos that is very dear to us as well. And we strongly believe in it as well. And I think that kind of just wraps up my presentation. Try to talk really quickly within 10 minutes. So I'll hand it over to the next presenter.
Yes, and the next
I think that was my last slide.
Next presenter is Bart Wouterix, who is CEO of the Sniffers. The Sniffers have 30 years experience in identifying, quantifying, reporting emissions from oil and gas companies. Bart and his team help customers to define and execute effective emission reduction programs. The Sniffers is an accredited organization and applies both bottom-up as top-down measurements. With a recent focus on methane emission, the company contributes strongly to limiting global warming. Bart, the floor is yours.
Thank you, Berenice, for the introduction. Let me start with congratulating GERG with its 60th anniversary and with this event. Thank you for having me in this panel, and I'm glad to share lots of experience to the solution. Next slide, please. A few words about the Sniffers for people that haven't worked with us. The Sniffers is a company already 30 years around. We are an environmental and integrity service provider with 2 key focuses, one about emission reduction projects and another about pipeline integrity. We are active all around the world, and we are executing several hundreds of emission reduction projects every year. It's with our focus on those niche markets that we are also able to invest in innovative techniques and contribute to lots of technology evaluations, and I'm glad to share several of these. As Berenice also said, we are a accredited company, and that helps us to provide quality results to our customers. Next slide, please. When we talk about methane emissions and closing the gap and reconciliating the bottom-up figures with a bottom-down figure, this is really about level 4 and level 5. It's about the aggregation of all fugitive emissions together with all the emissions from venting and incomplete combustions, and trying to match that with the one overall site measurement figure. In previous presentations, it was already mentioned that we should look for cost-effective solutions. well, my feedback would be that the most cost-effective activity is repairing the identified leaks. If we see in practice reductions of 70 up to 90% are possible within 1 year, this is the most cost-effective activity, and it will definitely drive a negative investment. Let me share a couple of learnings how we can close that gap between level 4 and 5. Where should we pay attention so that we do not have that gap? Next slide, please. When we talk about fugitive emissions, it's important to stress that if we want to derive at a reliable figure, a strong methodology, a rigorous execution, and dedication is really necessary. Otherwise, the result won't be reliable. You heard about those stories about an operator coming back indicating we only found 5 leaks, while in reality, a multiple of leaks are available if you do the survey correctly. Too fast execution, missed sources, incomplete survey, poor calibration, all these components lead to poor results. Hence, correct execution according to agreed protocols. And in order to reach that, I believe it's important that your service provider that you are engaging needs to be third-party audited or accredited. Next slide, please. Another learning that I like to share. Next slide. Another learning that I like to share is about the completeness of the surveys. This is an illustration for fugitive emissions where the complete PNIDs have to be inventorized and have to be populated with the right data to come to the right composition and the right response factors like they are necessary for the different methodologies. If this exercise is not done with a high level of quality, the result will be rubbish again. And hence my plea for a complete inventory. And this comment is not only valid for fugitive emissions, it's also there for venting. I've heard managers saying about their assets, we do not vent, we don't vent, not necessary to measure vented emissions, while in reality, multiple vents were of course available on that asset. Next slide, please. This slide is sharing a little bit of our learnings concerning the technologies that we are seeing in practice, and we see an evolution in the market. And I'd like to explain what is on this slide, describing a little bit. First of all, scenario A. Scenario A is a scenario where an optical gas imaging camera is used to identify leaks. And with those identified leaks, we are using leak-no-leak factors to come to a final figure. Over time, we see that this is not good enough. Leaks of 5,000 PM perhaps are identified, 10,000 with a higher probability, but lots of leaks are missed. And also the calculation with leak-no-leak is very, very inaccurate. A better scenario, and we see that happening with the more ambitious companies, a better scenario is where techniques are combined. Sniffing devices, FID devices are used for detection, identification of all leaking sources, together with the EPA protocols. And for the non-accessibles, we still use optical gas imaging to identify at least leaking non-accessibles. Lately, we see a next step to scenario C, where we still use a sniffing device for identifying all the leaking sources and using the EPA methodology to quantify those emissions. We're still using OGI for the non-accessibles, but we are introducing high flow sampling and bagging for the biggest leaks. The biggest leaks, just rounded up, 20% of the leaks are creating 80% of the emissions. If these biggest leaks can be quantified with a direct measuring method like high flow sampling, the accuracy of the total figure is increasing drastically. So high flow sampling, we see that happening, is used for what we call the pegged readings, the big leaks that are found within a fugitive emission campaign. The last months, we also see a scenario D, where also a quantified optical gas imaging technology is introduced. And this scenario D is identically the same to scenario C, with the exception that when we use an OGI camera to screen the non-accessibles, there will be a few that leak. And how do you quantify those leaks? There we can apply the quantified optical gas imaging. It's not too accurate, it's not too reliable to use for all kind of leaks, but when it comes to non-accessible leaks, this is a methodology that can help us to quantify. So the takeaway for this slide is really about combination of different techniques can help us to produce more accurate total figures. And the second remark that I'd like to make for this particular slide is in some of the draft regulations, we see references to using measuring methodologies that are capable of picking up a 500 ppm leak. Well, in that scenario, scenario A is not feasible anymore. 500 ppa with a camera isn't going to identify a single leak. Please go to the next slide. Jumping to venting emissions, I've heard that some people believe this is a costly exercise, but I don't agree with that. With venting emissions, to determine the emission factor for regulators, for valves, we are very instrumental in using high flow sampling and bagging, and can measure lots of venting emissions a day. This technique gives us a very reliable, based on this direct measurement method, a very reliable figure that we're using for all kind of venting emissions. On this slide, valves and regulators. On the next slide, next slide, please. An example for guided emissions through a small vent that is measured also here with bagging, with high flow sampling. We have pretty good experience in that to determine the emission factors that are necessary for the reporting. Next slide, please. The reporting as an example here, a TSO reporting where all the parameters necessary for an OGMP level 4 reporting can be filled in based on the methodologies that I just described. A few words about level 5. This is a completely other chapter, but I like to stress two techniques that weren't addressed enough, and I like to share some learnings with that. First of all, on the next slide, please. I like to mention the benefit of remote sensing networks. Placing around a certain facility, as an example, a small compressor station, if you spread 4 of those sensors around this facility, and they use pretty inexpensive solid state sensors that pick up methane. They can be installed pretty easily because they are powered with solar panels. They work with IoT communication devices, so that's pretty easy, that installation. We can grab that information pretty easily and use reverse dispersion modeling to determine the emission from the site. I like to stress the big benefit of this kind of installation because they are measuring the whole year. And especially with assets that aren't stable emitters but have some ups and downs, it is very nice to have this kind of facility and this kind of measuring devices to monitor that and to trigger directly an action. Next slide, please. Just as an illustration, you see these an example of these measurements with varying emissions, and every time a threshold is passed, this can trigger an action. And this also leads to pretty easy calibration between the different methodologies. The reverse dispersion modeling together with going into the site, there's a certain emission that is suddenly coming up, going directly with some bagging methodology to have a direct measurement and compare the two different results. And that also closes the gap. A next slide, and this is my last slide, is illustration about drones, and several other speakers already talked about that. The learning that I like to share here with the group is that when you do a drone campaign and a measuring campaign, have also some people on the floor that directly can identify with an OGI camera the biggest emitters, whether these are fugitives or vented, identify those emitters, and at the same day do a direct measurement of those emissions so that you can compare in your reconciliation exercise those different figures immediate. Otherwise, there will be always uncertainties about what happened that day. Was there a certain incident happening? Was there a maintenance activity happening? All those uncertainties are taken away if you execute the campaigns at the same day. With that message, I'd like to conclude, Berenice, my contribution here.
Thank you very much, Bart. I know, Lola, that you have a hard deadline. There was a question for you. Very encouraging to see this ground truth validation of release rates at TETI. As you put up more satellites, how do you see your uncertainty reducing? Do you have time to respond, please?
No, that's fine. So basically, the key, if I understood your question properly, is how do those uncertainties in terms of the measurements that we take? So you used the example that I showed with Total in terms of how do we keep validating those going forward. And the key here is also in terms of repeatability. So as we get more information, as we are able to get more data is so powerful in that the more data we begin to have, the more insights we begin to develop. And as I mentioned before, this is not working in isolation of just looking at, you know, the satellites in terms of tasking our satellites. It's also leveraging on the daily coverage as well, for example, on the public satellites, and using all that information, we begin to get more and more information to reduce those deviations, so to speak, or the errors. Another key thing is based on weather. So because of the continuous changes in the weather as well, cloud conditions, etc., the more you're able to task your satellites to look at various times and various seasons as well, the more you'll also begin to get some sort of aggregated information about what's happening on any particular site. So I'm not quite sure if that kind of answered your question, but hopefully that gave you a little bit of insight as to the plans going forward for more validation of those.
I have more questions for Christian. It was also for you. It's a question for satellites. How do you differentiate methane emitted from natural geological features like massive mud volcanoes and oil and gas infrastructure emissions in Turkmenistan?
So it's really about the location. So if you had several oil installations surrounding an active volcano, then it would probably be tricky. But usually you don't see the two in that close proximity. And as you probably noticed in the images that Lola and I were showing, these plumes of methane, they don't last forever. So it comes out, you can see it for maybe 4 hours, maybe 8 hours, but it's not going to last indefinitely. So we focus on these abnormal concentrations. We know where the energy infrastructure is. And so we look for the contrast against the background level, which could have a little bit from agriculture, a little bit from natural sources. But when we're looking at these examples, we're pretty sure that, you know, we're focusing on what originated from energy infrastructure.
Yes, because I'm looking at at the slide that you presented, Christian, and I was a little bit taken aback that when you see Europe and also the countries where the members of GERG are active, well, you see that there is no yellow on it. There is quite blue. So there's a little bit of question: what can satellites mean for us in the countries where the members of GERG are active?
So I think two sides to that. One is the imported emissions of the energy that is being brought into the European market, whether as pipeline gas or LNG. And second, it's going to be working with more with better sensors. So GHGSat has a lower threshold. If you focus on the transport network in Europe, hopefully not, but maybe we will see some larger sources. And as time goes on, we'll continue to get into a lower and lower threshold. So I would take it as it's a great outcome. The European network has much lower emissions than the networks in North America and in Russia, for example. So it should stay that way. But we can at least look at the imported emissions upstream in the supply chain and keep using the best available technology to monitor compressor stations, block well stations, and maybe at some point the sensors will be able to see the current level of emissions that may be happening.
Yeah, I mean, I can sort of buttress to what you've just mentioned as well, Christian, in terms of the fact that obviously there are, some areas, especially with cloud cover problems, etc., in Europe, etc. But the one thing to kind of mention, so obviously if you compare it to a place like Libya, which has sort of perfect albedo and you can get, really good readings. So, for example, with actually, Christian, you mentioned in terms of the threshold, but more so about the resolution as well. So when you're getting to a resolution of about 25 meters, the thing is you're then able to better isolate distortions because you're not looking at major big pixel sizes. You're able to kind of narrow down to much smaller pixel sizes, which gives you a bit more information, and then it removes that difficulty of you trying to resolve on a much bigger sort of pixel. And then again, the other thing to add to that as well is when you have a satellite, for example, that is very focused and it's not sort of multispectral, is very focused on methane, for example, then you have that option of when you're trying to do all the band subtraction and and all that kind of thing, you lose a bit of resolution. But the advantage of having those sort of those focused methane developed satellites is that because they're the gases have been tuned to pick up those absorption of the gases for methane, then you've got a little bit better chances of picking those up as well. So I hope that kind of helped as well to buttress on what Christian was talking about.
There is, and I think I'm going back to the presentation of case that, and it's something that as an operator, there's something that we are confronted with. When you have pipelines and you are underground emissions, so you have, of course, also the impact of the ground, and a little bit is a question also how accurate, reliable is the relation between the measured concentrations and the actual local emission rate, knowing that sometimes it's just under the ground. I don't know if the three of you can comment on that.
Berenice, when we execute lots of leak detection measurements for underground pipelines, so several thousand kilometers on foot, by car, by helicopter, and also with our dogs. The emissions that we find, or the leaks that we find in Europe, let's call it like that, these are limited. We talk about ppm levels. If we found a leak and we measure that in ppm levels, and if you would really quantify this, and there were some illustrations today, then this is about several hundred kilograms per year. The big ones we can find outside Europe. Yep.
So I don't know if you want to, Christian or Lola, you want to add something about that?
Not really on my side. I think that is really a job for people in the field, like Bart was saying. So this is I think an area where I don't have anything to add.
Yeah, and I totally agree with you as well. It's a case of there would always be those deviations, and it's a case of just using all of the information you have in a very cost-effective way, as I mentioned earlier on as well. So it's leveraging on all the information you have and tying that into, you know, ground measurements, OGI, etc., to just kind of close in on those sort of deviations that you get. But yes, inevitably, there would always be those sort of deviations.
Berenice, don't forget that most satellites do not pick up those smaller leaks. Yeah, we are using instruments. The sniffers is using instruments that start with 3 kilograms per year, and not per hour, per year, as a sensitivity. Big leaks are picked up, and then we talk about several hundred kilograms per year. Satellites are starting at a higher level, and especially if you have a spread out network, you do not have a concentration like in a closed facility where you have a multiple occurrence of potential leaks.
I know I'm taking the case, of course, of for example, a distribution network operator in a city like Brussels, to take an example. Well, it's a completely different situation than when you have a leak in the middle of an open space and yes, other kinds of emissions, of course. And that one, but it's still important that as distribution operators we also work on reducing emissions. We have to know that too, because it's not that sound the big ones, but we are working also on those ones.
And it's a combination of methodologies that are the right solution. It's not the one or the other, it's a combination. And it's leak detection with on foot, with the car, with satellites. The combination of everything can keep up that integrity.
Okay, in interest of time, I would have a lot more questions for all of you, but interest of time, we're already more than half an hour over over the schedule time. So I would like to thank you, all three of you, because it was a very interesting conversation we had here. The slides are everybody in the call can see the slides and will have the slides. So I would like to thank you, all three of you, for this. We have now a lunch break. I know that we are, Alexandra, I know that we are late. I'm really sorry for that, but we are half an hour late. Normally we start back at 1:30 and we'll have a second panel discussion. Thank you. And we have a second panel. This time we're going to speak about methane emissions and R&D. And I have 4 persons who are going to take part in my panel. First of all, Mr. Ziegler, Robert Ziegler, you are project leader methane emissions at the Joint Research Center for the European Commission. We have Tanya, we have already heard Tanya. At least we can say that you are an expert in the matter. I would say that's really the least that we can say. You, when I'm thinking of methane emissions, in many cases, then I hear Tanya. Then we have Jean-Daniel Paris, research scientist at Alternative Energies and Atomic Energy Commission, CEA. And then we have Mr. Paul Balcom, Division of Chemical Engineering and Renewable Energy at the Queen Mary University of London. So, let's start.
Yes, apologies. Bring up the slides.
Yes, please. Yes, please. And please, as this morning, please ask your questions via Slido. This helps us as and the secretariat who is really helping me behind the screen, helping me with all those questions and having them for our very interesting panelists. Tanya, the floor is yours.
Oh, I think we're going.
I know it's Robert.
Yes.
I'm really sorry, Robert. The floor is yours.
Okay, very good. Thank you very much. So. First, I want to say that the views that I express in this presentation are my own and do not bind my institution. This is one of the conditions that I had in order to join the GERG Advisory Committee and also this conference. So I'm going to not really give a presentation, but I'm more going to throw a few things into the room that may give some interesting discussion on the panel. So it's, I called it measure or estimate, some food for thought. And it may also be interesting from the political point of view, because I start with a quote from Peter Drucker, my favorite management guru, and that is that the number one business mistake is that you're running your business blind. That is pretty much the conclusion of his life work, I would say. So you need the information in order to make the right decisions in business, and in government, the same story. And I have here a very good comparison. One is this split of sources of methane that is published by this Climate and Clean Air Coalition, that is very influential in this whole discussion, obviously. And then next to it, the findings from an actual long-term survey, which was, to my understanding, the only proper survey that has been done over a larger geographical area worldwide, which was done by NASA and JPL, the Jet Propulsion Laboratory in California in 2016-17, over a 2-year period. And there you find that it's not agriculture that is the most important emitter in an environment like California, but you find it is actually waste management. A few super emitters in landfills actually are the biggest super emitters that they could find. And the next one was manure management. They have these feedlots in California where they use not straw-based but water-based manure management. So the Germans know the Gülle tanks, and the Dutch also. And they are very, very high in emissions, and they're also a good source for biomethane, obviously. And oil and gas was similar to the livestock sector, where the interesting thing is that California, once upon a time, was the largest oil and gas producer of the United States. I don't know, many people don't know that. But so they have hundreds of thousands of old wells. They still have significant production. I think now they are like number 3 or number 4 in the United States after Texas and North Dakota. And the others, the 7%, that also includes the abandoned coal mines that exist in California. So the interesting thing is that even worse than the ABC analysis about super emitters that we have heard before, it was just 0.2% of the infrastructure elements that were responsible for the super emitters and the majority of the methane emissions in that state. And so it was just 30 out of 270 landfills that made the landfills lead the pack. So this detection of the super emitters is really, really important, because especially if you think that there were 272,000 facilities and components that were surveyed, and just 0.2% of that turned out to be significant methane emitters. So this finding of the needle in the haystack, I think, is one of the biggest challenges that we have, and is the opposite, really, of a emission factor-based bureaucratic effort that some people want to make out of this. Okay, I mean, what is also interesting is that the majority of the oil and gas emissions were observed in a producing area, the San Joaquin Valley. You see here the picture, the old picture that I have on the left side. This was Los Angeles Beach a few decades ago. And so there is thousands and thousands and thousands of wells along the coast. The total number is probably in the millions for California, so much, much higher than the total well population in all of Europe together, that are abandoned now, and where there's this story that the abandoned wells gas a lot of methane, but that was not really the case as the survey found. What is very, very interesting also is that there was a shorter survey done by the same organization afterwards in the Four Corners region. The Four Corners region is one of the active shale areas, and also an area where there have been a lot of historic coal mining activity and other mining activity, because the deeper you dig, the more methane you will get from the geology. And in spite of this big difference, a rather depopulated area with a very different type of activity compared to California, the conclusions about the split in between the sectors are pretty much the same as what has been observed in this California survey. And so we've heard that before already, that the super emitters can be 10% of the total greenhouse gas climate forcing. So not just of the methane, of the total forcing, 10% from the super emitters. So we really have a big interest to do these comprehensive geographical surveys and find those. Next one, please. And so we heard already that a small number of high emitting sources have participated to this. And the most important thing is that there is a significant regional variation. So operating practices are different from region to region, which again makes the ideas of emission factors highly questionable, because it turned out not to be the same, even though you had the same type of facility in a different place. And the other important thing is that most of these methane sources were highly intermittent. They were not just seasonal, but they were also intermittent in the shorter term. That means that if I have like one survey or one satellite pass and make conclusions from that, is only the conclusion for that moment, but not for the next day, even, what the methane emission situation is. And so that means that if you want to do this right, you need a program that starts with a baseline survey that looks like this California survey over a significant period, seasons, different activity periods, and so on, at the entire country, and then regularly updates these measurements via overflights in a frequency of weeks or maybe months. And the technology that was used there was principally the Aviris NG, which is the JPL version of the DLR instrument that we have in Europe, which is a LiDAR instrument that is a real remote sensing for methane emissions. So it gives you a vertical profile of the methane emissions. So if you fly a few cross sections through a plume, you get the actual quantification. You don't have to simulate. You don't have to do Gaussian plume modeling and things like that. And in addition, it has all the important meteorological instruments on board, similar to also this German airplane that we have in Europe. And that is very important because I have an example from Poland where the biggest emitter there is a coal mine, which we couldn't see on the Topomi instrument, simply because it's a landlocked area, so the wind comes from all kinds of directions. And so when you then average the readings that you have from the satellite passes, you see nothing. If you look at individual ones, you see something, but this is the difficulty, obviously, because there can be a lot of artifacts that way. And so this is really the professional way to get to a proper methane budget and to a proper baseline study. And without this, you end up with things like I have shown before, where industry-associated bodies publish data which is in no relationship to actually what has been measured in a real survey of an industrial area that is very similar to Europe, except that it has much more oil and gas activity than we have in Europe. Next one, please. And so, quick word about the Permian survey. I don't need to read all of that. Here you have a picture of the nice landscape during the Permian, where life was abundant compared to today. And the difference there was that the Permian is export constrained, which means that you have a lot of events that occur because pipelines are lacking. So gas is being flared a lot more than elsewhere. The flares don't work very properly. Other emissions also occur because the infrastructure is not complete, not built out to the proper standards yet. It's very much a pioneering area. What is very, very important there is the data shows that the biggest emissions from the Permian were from unlit flares and from not well combusting flares. And now this is in a highly developed oil and gas area like the United States, where people actually put some thought into a flare construction. Now, the flares that I know from areas where I have worked in my life, in West Africa, in the Middle East, Algeria, for instance, this is just a pipe in a pit. And so you can imagine how much emissions you get from there, and it is certainly never close to the 98.5% combustion activity that is claimed by like the World Bank flaring project. And when you then think that about twice the annual consumption of Germany per year is still being flared, I would say that flaring worldwide probably is the biggest elephant in the room that should be addressed first. And I'm very happy that in Europe we are now going to regulate flaring very harshly in order to make this practice yesterday's story, because there are lots of alternatives now existing even for short-term gas use. Next one, please. What is very interesting also is that obviously now California has this superb data set that is presented in a GIS, where you can dig down to the most detailed level, get all the information very easily. But when you then look at the greenhouse gas reporting as it is done, and I take here the example from Ventura County, they ignore this data. So they continue reporting their emission factors, they continue reporting as per IPCC, and then have such lame excuses that super emitters are not properly defined, so therefore we ignore them. So there will also be a significant learning effect that is necessary after you have such a baseline survey for also the government entities that will have to do the reporting. Next one, please. I don't know, how am I doing with time?
I was on mute, so there is.
Yes.
It's okay. Please continue.
Okay. Yeah. So same thing here. You know, I mean, we have here on the again this same coalition reports that methane is 85% worse than CO2. But when you then go to this IPCC working group that actually is working on that and look at the key person who is working on the methane factors, this is a gentleman called Hu Sang from China. You find out that he makes the statement that the global warming potential greatly overestimates the effect of the methane. So it's nowhere near 80 times worse than CO2 in its effect on global temperature. And this I think should not be ignored. And he introduces the more complicated to calculate, but still far more representative global temperature potential. And there you find when we go to the next slide here, please. There you find that if you compare CO2 and CH4 on the 20-year time span with the global temperature potential, so methane is only like 39 times worse than CO2 suddenly. And this is still mass to mass, but this is a gas. CO2 is a gas, so we should look at gas volumes, and when that means that's a third of that, because cubic meter of CO2 weighs roughly a third of a cubic meter of CO2. So CH4 is much lighter than CO2, and then you will end up with something like 15 times worse than CO2 volume to volume. And the other thing is that everybody loves to talk about the 12-year methane life, but when you look at the actual key paper for that, which is the NISBET one that was published in the World Geophysical Journal, the technical lifespan of methane in the atmosphere is 9 years and not 12 years. So I think that it is very important that we look a little bit better at the real data that is available, and not at these perpetuating rumors where one pressure group starts claiming something and this gets adopted by everybody, and nobody looks at the real underlying science anymore, which is available from the IPCC and from these technical papers that are referenced in the IPCC technical reports. So I really recommend, I mean, this is 4,000 pages and it is crazy to go through this, but I really recommend everybody who is interested in this to go through it and draw their own conclusions from that, and then have proper technical arguments together with proper management, with proper measurement in order to make the point of what the real role of methane emissions are and what we have to do there. Because the last thing is if you look here on this statement, that methane is supposed, according to this organization, is responsible for 40% of the warming since the Industrial Revolution. So what was that? The British coal mines in 1860 that emitted so much methane that 40% of all warming is now due to methane. So this is all information that we should never allow to exist because it's completely unscientific and not based on anything that IPCC publishes or anybody else that is a serious scientist. Thank you. That's all I had to say, and I think this should give us some good food for a discussion.
Oh, thank you very much. Oh yes, there is a lot of things we can start a discussion on. But before that, I will let another of my speakers, I think the next one is Tanya. Tanya, the floor is yours.
So thank you very much, Berenice. So it's clear that methane emissions are in the spotlight. So we have seen this morning that there are really a lot of activities ongoing. So if we go to the next slide, so the European Union has taken an international lead role on the methane emissions topic. So last year in October, so they published the EU methane strategy to reduce methane emissions, not only in the energy sector, but also they are covering agriculture and waste. So in this strategy, so they announced that this year they will be working on a legislative proposal covering methane emissions from the energy sector. So we are expecting this proposal of regulation to be published now on the 14th of December. There have been also a lot of activities. So the European Parliament has been working on the strategy. So they have published their opinions and the report. So the report of the Parliament was approved in October. Also ACER, so the organization of regulators, the European regulators, have also been working on this, and they have published a report in September, in July, on their views on the strategy. Also, the European Union is supporting the oil and gas methane partnership. And so they are part of the meetings that we are having. So an important number of European operators have joined on voluntary basis this initiative. So to support the establishment of the reporting templates, the technical guidance documents, so to have the discussions on how the uncertainty and reconciliation of data will be done in the future. And so also at the end of October, so the European Union, together with the United Nations Environment and other partners, so they launched the International Methane Emissions Observatory. So that some colleagues have already mentioned this initiative. So at the moment, so they have already published the first report that was published at the end of October. They are covering at the moment oil and gas, but the next module will be on coal. And the idea is to extend this observatory also to cover agriculture and waste in the future. So to have the complete picture of the methane emissions. And so the thing is that, so it has been discussed this morning whether there will be a role for the verification, and in principle, so IMEO will be taking data from the industry, so for the OGMP initiative, but they also will be taking data from the national inventory reports, data from satellites, data from scientific studies, from independent scientific studies, and putting all this together just to have a verification of the data. Also in September, so the European Union, together with the United States, so they announced that they will launch this global methane pledge. They presented it during the COP26 in Glasgow. So there is a collective goal to reduce the methane emissions at least 30% in 2030 with respect to 2020. And so nowadays, more than 110 countries have joined this global methane pledge. So now, so this is a commitment, but now it's needed to design how this will be done. So how this 30% will be achieved. And so there is also the commitment to improve the quantification of the methane emissions using the best available methodologies. So if we go to the next slide. So in this slide, so I show the photo of all the things that have happened during the last month. So after the publication of the strategy last year, so there has been like a revolution. So meetings, workshops. So the European Commission has been gathering data from different stakeholders to prepare the legislative proposal. So the companies that have joined on voluntary basis OGMP that are at the moment more than 70, so they have provided their first reporting at the end of May, and so based on this, the UNEP has prepared this first report for IMEO. And so if we go to the next slide. But so what the industry is doing for fighting methane emissions. So I think it's very important to recognize that the role that the European gas organizations are playing, because so they are really doing a lot of efforts to support the industry to manage and reduce methane emissions. So I have to mention GERG, GIE, Marco Gas, also the ENSOC, Eurogas, energy community. So there is really a lot of support from the associations to the industry. So in this association, so we have been working on technical tools. So so some technical recommendations, glossaries, best available techniques. So many materials have been developed and published, and they are available for the industry to use them. Also, a lot of workshops and seminars and training sessions have been organized for sharing knowledge and raising awareness. And it's unbelievable how the industry is open to share their current practices for others to learn. Also on the MRV part, so the monitoring, reporting and verification of methane emissions. So there has been an important movement from the industry to support OGMP to prepare the reporting template, and now also for as I said, for the preparation of the technical guidance documents and how to reconcile the data and to improve the accuracy of this data. And also on the research and development part. So we have seen already this morning a lot of projects, and then I will also give some additional ideas at the end of this presentation. So next slide, please. So I have included this here. So 1 month ago, so these associations, so they have published one joint declaration showing the joint efforts to continue reducing methane emissions and also to support the global methane pledge that was announced. So this document contains key figures and facts. So it gives an overview on the international initiatives such as the OGMP and the methane guiding principles. It contains in part also on the research and development, and includes also an overview of tools and videos. So if you have not seen it, so there are a lot of good materials there in case that you want to check it. So I have included also the link. So next slide. So on the challenges that the industry is facing nowadays. So it's clear that you can neither manage nor improve what you don't quantify. So I have adjusted the sentence, but this is the idea. So I still remember several years ago when we started the discussion among the different companies. So we were asking, so how do you quantify your fugitive emissions? And some companies were saying, I don't have fugitive emissions. How is possible that you don't have fugitive emissions? Because I'm not using any equipment to detect and I'm not following any procedure to quantify them. So therefore, it's really important that the industry has tools for the quantification, and so that all of us are well aware on the methodologies for the quantification. On the selection of technologies, so there are technologies, so both bottom-up or source level and top-down site level. So now, this morning, so the GERG projects have been presented on this. The industry, so still we need to continue working on this. So just to see what technologies are available, and there will be, so this is evolving also very fast, and there will be additional technologies in the future that we can use for both for detection and quantification. Also, it's clear that the satellites will play a role for the verification of the emissions. So nowadays, due to the capability, so due to the detection limits that they have, it's not possible for the current satellites to detect or to quantify the methane emissions that we are having in mid and downstream assets. But I think that looking to the evolution that they are having, this will change very fast. So on the data reconciliation, So all the companies that have joined on voluntary basis or GMP, and now once we will have the regulation in Europe, so we will be doing the reconciliation of bottom-up data and top-down or site-level data. But so this is one of the biggest challenges. So there is a lack of experience. So it's clear that in the past we have been using mainly the bottom-up approach for the quantification of our emissions. We are having discussions on the frequency for doing the measurements, on the sampling of the different assets that you need to measure versus the population that you have. In case you have, for example, 100 regulating and metering stations, so what is the population that you have to, or what is the number of assets that you have to measure just to have a clear number? And then, so we have seen this morning also that the technologies, so the current available technologies have constraints and limitations. Also on the emission factors, so Marco Gas is currently working on a database for emission factors. So we need support from the industry to continue working on this, to have specific emission factors and stop relying on generic emission factors that you can find in the bibliography. So also Berenice mentioned this morning the correlation factors. So nowadays the best available tool that we have in the industry is the European standard 15446. But these correlation factors for calculating from the ppms, for converting the ppms into a flow rate, were not designed for the gas industry. So it's true that it's the best tool that we have, but we need to work on this for having our specific correlation factors and to reduce the error that we are having with these factors. Also on the technical standards and guidelines for helping the industry to improve the harmonization on the different practices for the quantification of methane emissions. So at the moment, SEN is working on a standard that will help the industry on this, and so this will be key also for all of us. And next slide, please. So some final thoughts from my side. So raising awareness and sharing knowledge to build a culture of curbing methane emissions is key. So we have seen that the workshops and webinars, so in for example, this conference, so they are really supporting the industry in learning and having a deeper knowledge on what they have to do. So the investments and costs, so an important part of the European gas operators are regulated companies. So therefore the costs associated to this need to be recognized by the national regulatory authorities. So we have seen now a new target, so of this 30% in the global methane pledge, but it's clear that this is new for the industry, that we have been doing efforts and investments for reducing our methane emissions in the past, and these previous efforts should be recognized and fairly accounted for. So the actions, so they should be prioritized, so based on the cost efficiency. So at the end, so all of us are minimizing our methane emissions, but we cannot lose the cost efficiency perspective. So the flexibility and recognition that one type of solution doesn't fill all type of assets and situations. This is clear that there is the legislation that will be published, the proposal of legislation that will be published now in December should not be very prescriptive and should give the industry flexibility on choosing the best practices or the best technologies that can help the industry to minimize and to mitigate their emissions. And the final point, so the R&D is key to overcome the challenges that we are facing nowadays, and that the GERG projects that we have presented this morning, and also the methane roadmap that will be published today are very timely and will support us to continue in this challenge that we are facing. So that's all from my side. Thank you.
Thank you, Tanya. Next speaker is, I think, is Jean-Denis, the next speaker.
Yes.
The floor is yours.
Thanks. Can you hear me properly?
Yes.
Okay, so thanks a lot for giving me the opportunity to speak here today. It's really a great opportunity. And by looking at the list of panelists that would have been talking before me, I was wondering how to give a slightly different perspective. And I wanted to take the point of view of atmospheric measurement actually, and give it a slightly different flavor from what we can see in site level measurements. So I'm a research scientist in a public research lab at LSCE, and we have since a long time a lot of activity at the global level. Methane, we measure methane in the background atmosphere since many years, and this has led to contribution to, for example, the IPCC report. Next slide, please. And I think it will echo a little bit the discussion of Robert on the GWP versus GTP. So the last IPCC report take in the summary for policymaker take a slightly different look and start from the observation of 1.1 degree increase compared to pre-industrial over the last decade. That's the panel on the left, and on the panel on the right, you see the attribution of this to different species. And so you have positive contribution from carbon dioxide, methane. You have negative contribution, for example, the aerosol cooling effect. And if you look at that more closely, you see that the methane, the combined effect of methane is 0.5 degree in terms of contribution. So it's not a metric that helps to say which one is stronger than the other, but it shows a little bit in the perspective what is the responsibility of methane. And clearly there is a great advantage to prioritize methane emission reduction, because it also come with a lot of other type of advantages. Next slide, please. And so I have stolen this slide also from Valérie Masson-Delmotte, who is the rock star in my lab, and she's the lead author of the IPCC Working Group 1 report. So clearly, it identified that methane is a strong priority because it has a positive air quality impact. If you reduce CO2 emission, you would reduce a lot of. You would reduce also the aerosol cooling effect. So the immediate warming effect would be slightly mitigated. Whereas with methane, you reduce directly the radiative forcing, and you also have a collateral air quality benefit, which is really nice for everybody. Next, so let's look a little bit closer at the methane. You have probably seen this type of slides already. It's the recent synthesis by Marielle Senoy, also a scientist in my lab. But of course, it's a very collective effort, like the IPCC report. So it's a global carbon project synthesis on methane, and it shows a view of which sources on which sink are important. We will talk about sources mostly here, and it highlights the importance of agriculture and waste I look on the anthropogenic side, and also fossil fuel production and use. But if you look at the two type of estimates, bottom up and top down, and it's actually not the same type of top down and bottom up as we are discussing when we look at site level emission. Here, the bottom up is either it's based on the global modeling, taking a mechanistic understanding of phenomena, or it's based on inventories, looking at aggregating individual emitters to reach a global or national scale. On the top-down view is the integrative property of the atmosphere. When you make atmospheric measurement in the atmosphere, either from a satellite or from a network of stations, you observe, you can attribute the increase in concentrations to different sources. And when you try to reconcile this top-down and bottom-up, again, top-down, bottom-up reconciliation problem, you get very different numbers, and it really shows where the uncertainties are located. On anthropogenic sources, we still have a lot of these discrepancies. Next, please. And so thanks. So there has been a companion paper by Jackson and colleagues together with the paper of Marielle, looking at the reasons for methane increase, so not the dynamic of the signal, and trying still to keep this view differentiating top-down and bottom-up. So over the last decade or more, slightly more, they identified that there are two main components of a global methane increase: it's fossil fuel and agriculture. But if you look at top-down and bottom-up, the funny thing is that they will tell you the different response about which one is ranking first in responsibility for increase. That's the panel on the right. If you look at the brown bars, it's a fossil fuel. The blue bar is agriculture and waste. On the slight shade is top-down. On the darker shade is bottom-up. So again, we have very different response if we take inventories on models, the bottom-up view, or just look at the gradients in the atmosphere that we measure, and this is the top-down view. So clearly, the increase is attributed. Some big component are the coal mining and usage in China. It's a very big component. Also, there are a lot of discussion about the impact of a recent regulation by the Chinese government to reduce the exploitation of high methane emitting mines, and also to promote utilization of methane in mines. But still, it's a slow effort, and the production has increased, so it's continuing to increase emission. If you look at North America, there is also a strong fossil fuel component, which is mainly what we have seen before with the Permian Basin on all these large exploitation region. And then the agriculture component is more widespread over the world with maybe less super emitter, let's say, or super emitting basins. Okay, thanks. Next. Okay, but so the Elisa Oko from Environmental Defense Fund has put together recently a paper trying to look at what is actionable, what is more actionable in terms of emission reduction. And so she has differentiated what is economically feasible in terms of mitigation. So that's the low-hanging fruits. What is technically feasible, but would require a lot of incentives. On what are the residual emissions that we cannot change unless we change deeply the lifestyle on model of current economies. So actually what happened is that the oil and gas sector is the lucky sector with the most economically feasible reduction possibilities, whereas it's much more difficult in agriculture in general. Where you have very little economically feasible mitigation, and so it would require a heavy investment to promote lower methane emission for these sectors. For the oil and gas, there are a lot of on the first one is avoiding leak, of course, but so the paper is getting more detail about this. But we need to accompany these developments. To show a little bit more what is the baseline against which we can estimate the mitigation effort, and what is the actual mitigation achieved. Next. So I take a few samples of work that we do in my team. So we have been looking at the emission in France for the Ministry of Environment. And we take, there are a lot of inventories that you can look at, sector by sector, country by country. And so for France, we have tried to revise the national emission inventory against atmospheric observation. So what we see first is that there is a big underestimation for agriculture. You see, so for people who know France, Bretagne on the western part is still deeply underestimating the emission for agriculture. And overall, the increment is also reducing strongly the emission for the Paris area with less anthropogenic emission. Actually, if you look at the bottom left panel, you see that the different inventories are in red on the different result of the optimization that we provide. So it's called atmospheric inversion. We use the network of stations and we use an atmospheric model to optimize inventories so that they match the atmospheric measurement. And we actually see that overall there is a huge underestimation of the national inventory. And when we arrive with this result, we cannot call this really verification. We are not verifying things. It's not. I would not go to a lawyer and oppose this data to claim that we have the right answer. But it's really promoting an effort to revise the inventories, revise the emission factor on activity data, and also to reach this sort of conclusion, we need to have a transnational network of measurement. You see on the middle bottom panel, it's a different measurement station that we use to provide these results. On the darker the color, the more weight the measurement site has in the result. So you can see, for example, that there is a station in the Netherlands that without it, it would be difficult for us to provide the results for the French inventory. It's a very interesting transnational effort. So in Europe, we have ICOS. There are other networks in other continents, and we are really strong promoters of the ICOS network. Next. Going a little bit more local, still visiting France together. This is a recent paper that was published by Sarah de Fratica. She was doing a PhD with me, so we went driving 700 kilometers in Paris and measuring methane isotopes, and also with handheld device. And we tried to see what are the main sources of methane in Paris. So the first thing we found is that we are really so compared to the big database of cities that have been already described, especially in the US, Paris is actually quite clean. There is very little, a very small amount of peaks that we detect in the city measurement. But also we discovered the importance of the sewage emission and also the furnaces, so in buildings, the building appliances. And actually, after we published the paper, we were called very quickly by the official, the group that prepares the official inventory for Paris, because they were not able to take into account the sewage on furnace parameters. So it's really interesting to see that going on the ground for measurement always teach you nice lessons. Next. So we try to go a little bit further on develop with measurement, do our own top-down and our own bottom-up, and finally go for reconciliation. So we have the chance to have a collaboration with Cyprus, where we have a little bit of resources to perform these measurements. So we have a top-down approach with aircraft. We fly around the island to capture let's say, the exhaust of the island. Mainly for methane, essentially. And then we developed our own bottom-up with so going from site to site. The good thing in Cyprus is that there are very few natural sources that disturb our measurements, and the number of landfill and farms is relatively manageable for measurement. So we drive a lot. So we use the bicycle also when we are fed up of driving. It happens sometimes. And we are trying to develop a methodology to reconcile the two and provide some useful data for the baseline emission pattern in Cyprus. Next, please, which is interesting because Cyprus is going to buy floating storage and regasification unit to change its energy, its national energy provision. It's essentially fuel at the moment. So they are supported for that by the European Commission. They are going to buy these ships, the Galea, and they're really interested to see what is the potential change in the structure of emission after that. Next. At a more regional level, also we try to using also atmospheric measurement. We try to see what are the emissions. And we had a campaign recently that sailed typically. So I show here a result for the Arabian Gulf or Persian Gulf, depending on your preference. So we show very unambiguous misestimation of emission. And when you are in the southern part of the Arabian Gulf, there is a strong overestimation of emission. And this is where you have the Kars gas field and the very important resources for natural gas. And when you arrive in the north of the area, which is on the right of the time series, when you're in the north of the area, you have much more oil wells, and in this area, the emissions are clearly underestimated. So clearly, there is a lack of accounting in the inventories for the economic value of gas, which promotes maybe less leak than thought in the emission factors. And on the opposite, in the oil area, there is maybe less controlled flaring or poor flaring, and finally a lot of release of methane to the atmosphere. And we determine a little bit where it comes from with we use a series of tracers. We use alkanes to look at where are the methane emissions coming from exactly. So here I show the example of the C5 isomeric ratio, so IC5 to NC5. And it's interesting because with the ratio that we see typically in the Arabian Gulf, we are close to the value for natural gas. Actually, when it comes from urban area, so from how to say, so from gasoline for engine, the industrial process of a refinery changes the ratio, and you can use it as a tracer to see the origin of methane enhancement. So with the suite of volatile organic compound measurements, we can also trace which part of the value chain is emitting the methane. Next. Oh yeah, and this is the nice nightlight view that you have when you sail in the Arabian Gulf. You see the city lights as a sharp light, and all the halos of light are the flaring points, and it's really exactly where we see the emission. It's very nice thing. On the next slide will be my last one. I just wanted to say, so it's a little bit further away from the discussion that we are having now, but one of our newest research projects is to go and detect methane emission from the ocean. You have natural process dissociation of methane hydrates that we have developed eddy covariance technique to detect this in the Black Sea. I think it's interesting also to mention that because you have with offshore geological storage for methane, you may have a challenge measuring potential leaks. And there are no actually good techniques for that, and maybe what we are developing here might be useful at some point. I just wanted to show a nice picture of a gas hydrate in a calcified extract from the sediment here to finish on this picture. Thanks.
Thank you very much, Jean-Denis. And now I'm giving the floor to Paul Balcom, who is going to finish this as the last speaker before I have some questions to all of you.
Brilliant. Thank you very much. I've just taken control, so hopefully, does this work? Yes, it does. Fantastic. Yes, so thanks very much for inviting me. I'm Paul Balcom. I'm at Queen Mary University of London, and this is a little bit of a rundown on a few of the projects that we are doing at Queen Mary relating to methane specifically. I started quite recently a new research group in this area called the Low Carbon Gas Supply Chain Research Group, and so we do lots of stuff, and it includes it's an interdisciplinary group which includes measurement experts and also mechanical engineers, and also economists and policy experts. And so the idea is that we try and tackle this because you need to look at it from various perspectives to understand how best to reduce. So we do lots of work on in the field of methane monitoring and reduction, and also we do a lot of work on hydrogen and ammonia supply chains too, but that's less relevant to today. So, so yeah, I'll go through a couple of the projects that we're working on and in the future. And the background really to this is that we've seen loads of progress in terms of methane measurement and understanding across the natural gas supply chain over the last 10 years and more, but it's really sped up in the last 10 years. But primarily the focus has been on sort of upstream, midstream, and there has been much less focus on LNG. And so our sort of primary focus at the moment is on the LNG part, where we see some pretty significant data gaps. So we've seen a reasonable amount of work gone into upstream, midstream, but we see in terms of published primary measurements of methane emissions, there's hardly anything in terms of liquefaction and regas, and there's almost nothing on the LNG transport side of things. So we're looking at LNG carrier ships primarily, but also LNG fueled ships as an end use. And so I think the risk here and the importance of this is that the current assumption is that we have very low emissions from LNG transport, but some publications have started to contest this, and so it's really important for us now to develop some independent peer-reviewed publications and primary measurements and understanding of our methane emissions, so that we can either corroborate these low emissions or so that we can work out how best and how much we can reduce our emissions by. So the studies that we've particularly been looking at recently are on the LNG carrier ships side of things. And so in terms of what we know about LNG carriers and their emissions, the sources of methane emissions are very similar to the sources of methane emissions that you're likely to get in the other supply chain segments. So we sort of divide them up by the vents and fugitives and incomplete combustion, but perhaps most pertinent to LNG carrier ships is engine slip. So part of the incomplete combustion, whereas normally we'd think about flares, engine slip is particularly important. So some of the gas that's being transported is used as a fuel to propel and to power the ship, and part of that slips through the engine and is emitted to the atmosphere. And in terms of what we've got so far, in terms of primary measurements and published data, we've got a little bit on engine slip. We've got a few measurements of engine slip, but we've got pretty much nothing on vents, fugitives, and sort of maintenance activities. And so there's a real data gap that we need to start filling in. And this is just a little graph of some of the data that does exist at the moment. This is a graph of methane slip across 4 different engine types of gas engines, and so this is sort of some of the primary data, which is very useful, and it kind of tells us a little bit about what the variation in methane slip rates are across different technologies and different ships. Probably really important to this is that the engines on the right hand side, so the 2 engines on the right hand side, which has hardly any data, are the main LNG carrier engine types for new vessels. And so we think that they're fairly well performing, but we need to corroborate this. And I think the key importance is that we need to get measurements of in operation LNG carriers. So we don't just want to rely on testbed data on performance in a lab. We want to actually understand what the methane emissions are in operation in the real world. So we're trying to rectify this, and this year has been an exciting year for us because we've gone on board our first LNG carrier ship to do a quantification of total methane and CO2 emissions from an LNG carrier ship round trip. So this is the first time we believe that somebody has tried to directly measure methane and CO2 emissions from a total methane emissions from a total perspective. And so this is a first of a kind, and this is the first ship that we have been on. And it's the idea of this is to do a whole round trip, so including the loading operation of the gas, including the cargo transport, including the delivery and the unloading at the destination port, and also including the return trip. So we want to understand what the emissions are across these different voyage segments. And also, we really want to know, how do we most effectively measure and estimate methane emissions from LNG transport? So this is just one ship amongst many, and so we're not claiming to have solved the issue by any means. But what we really want to do is work out, how do we most cost effectively measure in the future going forward? So the ship that we selected for this first measurement was a very new LNG carrier ship, which is the Gaslog Galveston. We went on board. There was three of us as researchers went on board in March this year, and we did a route that took about a month from the US, so around Corpus Christi, going to Belgium, and then back to the US again. And so this was definitely classed as a bottom-up measurement study. So we actually used some continuous emissions monitors for the engines and for the exhaust stacks. And then we also used OGI cameras and high flow samplers to detect and quantify emissions from fugitives, and also from vents as well, which we also relied on some of the flow meters on the ship as well. And so I unfortunately can't tell you a massive amount about the results, because we haven't we haven't published them yet, so they are due out imminently, and I'm sitting on a version of the paper right now, so I'm quite excited to get this out, and I shall tell you about it as soon as I can. We're nearly there, so I'm hoping to submit end of this year or beginning of next. But it will definitely have some interesting results, and I think the key thing here is that we need this type of study to really get an understanding of where our emissions come from. We know there are going to be some emissions, of course, across all ships, but we need to understand why they happen, and how, more importantly, how can we reduce them? Because we think that there will be some really easy wins in terms of methane emission reductions that may even be zero cost. So particularly from an operational point of view, and part of this story is going to be around how we can raise awareness from a ship operational point of view of how to minimize emissions. We think there are some quick wins here. So once this project has actually been delivered, the next stage is to plan to get a more representative sample of the fleet. So the fleet of LNG carriers is over 550 ships now. So it's a pretty mixed bag. It's quite a heterogeneous population. So we've got different ships of various different age. This is a graph that I've taken from the IGU World LNG report. So they're different ships of different age types, of different sizes, and also in terms of different engine and propulsion types. And so we know that we're going to see different variable emissions across the different across the fleet, and so the idea is that we need to cherry pick what are the most important technologies and operations to look at to really get this broader understanding of what our emissions profile looks like, and then therefore how we can reduce them most effectively. So I'll go into it. Maybe just I'll brush over this a little bit in terms of the measurement methods that we want to get into. So I think it's really important primarily to look at the engine exhausts. So when we're thinking of LNG ships, it's really important to look at both the main engines, which are providing the propulsion for the ship, but also looking at the generator engines as well. So the generator engines are the ones that provide the power, the electricity for the ship, like chemical plant, for example, and the power for the other accommodation, etc. And you're likely to see different emissions associated with these different engines, and so it's really important to get an understanding of the profiles across the different engines. We should also make sure that we look at the gas combustion units, which is basically the flares for the other parts of the supply chain, and also the vents. So there are often various vents across the ship for different duties across the storage and across the engine room, and obviously fugitives. And the reason I mentioned these different these different sources is that when you're on board a ship, if you're trying to measure from a ship, the measurement techniques might be quite different to those that you would want to employ onshore. So, for example, there's been lots of talk of satellite measurement. It becomes a little bit difficult when you're at sea. Not impossible, but very difficult. Also, you're dealing with a moving ship, often with high winds, with different emissions of gas at very different temperatures as well, which causes an issue in terms of measurement. So you've got cold vents, you've got cold fugitives, you've got warm gas, and you've also got hot exhaust gases as well. So finding the right measurement, the combination of measurement technologies is a really important task. And so going forward, when we think of getting our representative sample of ships, what we really want to do and what our plan is to combine a few different methods. So we need more bottom-up methods like what we've done in this current ship. We need more of these because we really want to understand the point sources. We want to understand much more accurately what our emissions are and conduct some downstream modeling to understand why we see the variations in emissions that we see, so that we can identify what the best reduction opportunities are. For example, are they just to use different types of engines or storage technologies? Are they just to change operational profiles? Are there some other aspects that we haven't even thought of already? So I think what we'll need to do is combine our measurement exercise with the shipping expertise. So we need to involve marine experts as well to understand what is feasible in terms of our reduction opportunities. And so we want to combine these with some top-down measurements as well. And by top-down measurements, really what we would be focusing on are sort of drone and airplane measurements. And so this definitely represents a difficulty in terms of logistics, in terms of legal aspects, in terms of permissions, but we are getting there in terms of working out how to do it. And this is going to be quite important for us from two perspectives. Really, firstly, to corroborate our bottom-up studies, so to make sure that we've caught all of the emission sources that we think we've caught, but also to get more samples, so to get more ships. So we think with some of these top-down measurements, we'll be able to get a larger volume of case studies. So the last thing to say is that the importance of what we've already got in terms of ship emissions monitoring. So lots of the ship operators are already aware to some extent of the importance of methane emissions, and some of these ships already have methane monitoring on board. Some of them are just from a safety perspective and not particularly suitable for quantification or for detection from a climate perspective, because we're dealing with much smaller leaks. But some of them have, for example, methane monitoring on their exhausts, and so we need to be utilising these because they offer up low-cost, longer-term sampling of our ships that we really need to get on board with. Pardon the pun. And so the whole idea of this is to develop a better understanding of the different emission profiles across different technologies and operations and ship types. If we get this, then we'll be able to estimate much better total emissions from our LNG fleet, which is something that's sorely lacking at the moment, unfortunately. And then the name of the game is to identify effective reduction opportunities and actually quantify how low can we get in terms of our methane emissions. So that was quite a brief rundown of our sort of current and future LNG project. I just wanted to mention one other project that's quite interesting and relevant to you guys. This is a project that we're about to finish. So it's by Maria Olchak, who probably many of you are friends with and aware of already. So she's a research associate at Florence School of Regulation, but she's also a PhD researcher with me at Queen Mary. And she's finishing up a really interesting study, which is policy focused, understanding how can we produce an effective MRV and methane regulation for the EU and more broadly as well. And she's doing this by conducting quite a wide series of stakeholder interviews across the range of stakeholders, so including policy experts, including the suppliers, including all sorts of stakeholders, to really identify what are the key barriers to actually producing an effective MRV, kind of in parallel to the EU draft regulation that's about to come out. So the idea is that we will be identifying the barriers and suggesting ways to mitigate these from a detailed perspective, and also to learn lessons from other regional experiences. We know that we can't just map on other countries' regulations onto to different regions, because some of it just doesn't apply. There will be different barriers and different opportunities, and so the idea is to produce firstly a critique of what we've already got in terms of our EU regulation, or what we will have in a couple of weeks' time, and also to make recommendations for increasing effectiveness more broadly. So with that, I will leave it there, and thank you very much.
Thank you very much for your intervention. I have some questions. I see there are some questions coming up. There is one for Jean-Denis, and there's three for you, Paul. I think some easier is, the first one is does the shipping project you mentioned for the LNG carrier include the regasification stage at the final destination? Second question, will your paper on LNG carrier emissions be available under open access license? I really think it helps to spread the findings. And the third one, which kind of sensors are you planning to use in drones and planes for these measurements? Passive sensors should be excluded because not suitable.
Okay, fantastic. I've forgotten what the first question was, but I'll go from the second one, perhaps. Okay. Actually, just remind me what the first question is, and we'll take
it. Was if it includes regas at the final destination or not.
Right. No is the answer. So what we're tackling is the loading, the transport, and the unloading. So unloading of the LNG, but not the regas. Necessarily. So we were just looking at it from the ship perspective, really. So for this current study, we were looking at just the emissions on board the ship associated with those activities. So we weren't able to get into the facility to actually look at the emissions from the facility side as well. But in the next round, we would seek to incorporate that as well. Whether we include regas, I'm not sure if that is going to be part of the scope. It's big enough scope as it is to get so many ships. But yes, so that's probably excluded from the scope, I think.
The key thing is, did that ship have a reliquefaction plant on board, and the cooling down loading facility? Did that one have a gas capture and reliquefaction for the cooling down? Because I mean, those are the two big steps where you lose methane in the LNG process.
Right, exactly. So that's a really good question. So that really depends on different ships. And so for the one that we looked at, yes, it does. So it was a modern ship, and it does have a reliquefaction plant on it. The interesting thing, I can't say too much about it at the moment, but the interesting thing was that the storage technologies, the modern storage technologies on the ship are so good, it's so effective that we didn't have enough boil-off gas to turn on the reliquefaction plant over the whole journey. Because we used enough in the engines and
but that was across the North Atlantic, so it was cold water also.
Well, that's true, but also you've got to understand that you stop for multiple days at the port to do the loading and to wait for your time slot. And so even when you're not moving, they didn't produce enough boil off to warrant using the reliq. But yes, and so different. There are some ships do have reliq plants and some don't, and so that might be quite an interesting part of the next study to understand if that has an effect on total emissions.
Yeah. And especially for the Qatar-Japan route, this is very important to have that reliquefaction plant.
Absolutely.
It's all tropic. If you go the Northern Passage out of Russia, you probably don't even have to liquefy the gas, it liquefies automatically.
Right. Absolutely. So in terms of the top-down study, so we are yet to select the specific technologies. We will be so I can't really sort of confirm what sensors we'll be using, but we'll ensure that they're accurate enough for us to produce a decent estimation, because it's going to carry quite some uncertainty in terms of the method that we use anyway. So we'll be using the most accurate. We'll be working with probably University of Manchester, so Grant Allen from there, who's an expert in drone methane measurement and has quite some experience on that, and also a company called Surveyr who are getting on board with this stuff. I think I'm missing a question that I've forgotten again.
There was a third one. It was if you were going to make the results available under open access license, because it was interesting to spread the findings.
Yeah, absolutely. That's the most important question is that yes, we will. The whole point of this is to publish real data and insights, and so we want to sort of make it open to all. So yes, we'll be publishing open access. Absolutely.
Then there was one for Jean-Denis, which were the most interesting or conclusive takeaways from the reconciliation exercise you mentioned in Cyprus?
Yeah, thanks. This is Jean-Daniel.
Sorry. Sorry.
No problem.
Sorry.
Sorry. So nothing really conclusive because it's still work in progress. But interesting, I can say two things. I think the first is that we don't have a lot of emitters like in the US to make a nice statistical distribution, but we have also the notion of super emitter on the main. The most intense emitter is actually a landfill that happens to be illegal since many years. So it's really difficult to account for it in the national inventory because it's considered as an inactive landfill. But in fact, it is, well, when we were there were still quite a lot of trucks. So if you want to do something that looks official in the end, you have to reconcile your own bottom-up with the national bottom-up. The second thing is that there are a few complexities to the exercise. Of course, the methodological one, of course, but also you have some. You have plenty of interesting but intense methane sources like dams used for agriculture that are just temporary and are dried when there is need of water for agriculture, and so they emit methane for a few months. And if you are not there on time to make measurements, or if you don't know the exact time of the exploitation, you miss the duration of the source. So yeah, mostly this part, I would say, that are the main finding. And also trying to escape the guards with dogs who don't understand why we make measurement around their industrial sites.
And as last question for all of you, I have an open question. It's, as you've seen, members of GERG are very keen to engage in projects around methane emissions reductions. Well, I suppose that you've seen all the presentations from Tanya and Christina this morning, the most current projects, and you've also seen a presentation of our roadmap with our research priorities. What would you think would be the important projects we could engage on a short time scale? And I would say the second one, something that Murray said already this morning, collaborative research is important. And how would you see this part? How would you see this collaboration with us as members of GERG who are interested in working on those projects? Perhaps I'm going ask you one by one, Robert.
Okay.
To start with you.
Yeah, I mean, I think that the most important thing is the baseline survey. Yeah? I think that we absolutely need a European methane baseline survey similar to the one that was done in California. We have the means in Europe. We don't have to bring it from overseas. Yeah? It's all ready to go. Basically, for day rate is available. Nothing has to be built. Yeah? And then based on the findings in this survey, we then can come up with a monitoring scheme that then everybody can agree on. Because at the moment, what I see is that everything is going very fast except the data collection. Yeah? So we have even now a methane observatory, but I don't know what they're going to observe because I don't need anybody to observe emission factors that are purely out of thin air. There's no measurement background behind that. So I think that this is the most important thing, and it's only with a proper baseline survey and then a regular recurring survey scheme can we have an educated discussion. Otherwise, you're going to have all these wild claims from one side and no claims from the other side. So this is not going to help anybody. So I think it's the data that we first have to provide. Without the data, everything else becomes useless.
And collaborative, how do you see that?
That is a joint effort. I mean, this is obviously not something that GERG alone can finance and so on. This has to be something where you get obviously permission from all members, also the non-members in the EU, because I saw there are some that are non-members, and then come up with this European survey, not only for the European survey, but because this also is then going to be the key export product to convince the non-signatories on this methane pledge and so on to sign there, because they will be treated fairly, because this is a method that has been afterwards accepted by everybody, verified and so on. Because when you now look, I mean, we all talk about, oh, we've got 100 countries signed up for that, and I don't know how many companies signed up for the methane partnership, but when I look at the list, there's not a lot of production behind that, and there's not a lot of methane emissions behind the countries that have signed up for that. So the big emitters are all missing, and the big producers are also missing. And they will only sign up if we have something really credible to offer.
Jean-Daniel?
Yeah, no, it's very, very good question. So I think to a large extent, I agree with Robert. The baseline is key here in the landscape of emission that we have. The baseline is important, but the baseline also in terms of induced emission elsewhere, not only on the European territory, because we consume gas from Russia, and from various other places. And it has been mentioned by Kairos this morning. I think it's extremely important to have some ability to monitor emissions along the value chain. I think also it's important, so third thing, it's important to look at how is it going to happen to monitor the progress. Because going with an OGI camera or laser instrument from time to time to a site will not really tell you if your effort has been worth it. It will just give you another snapshot, and you will need many different snapshots. And I think that in the exercise, the fixed sensor have a large role to play. Maybe combine so where you need sensitivity, so minor emitters. Let's say mostly in Europe. A satellite will have to play a role. And probably an array of measurement techniques in between on some integration capability. And for that, so we have this experience for CO2. It took us 15 years to start to articulate these principles of baseline and eventually progress against baseline. And to look at what techniques are needed for that. And so I guess here it's really important to start because there will be trial and error on starting to look at fixed sensor campaigns, satellites, on how it can be articulated together to follow progress. I think that will be the key. And if you look at the collaborative part afterward, I mean, we have it may not have to be an effort that fully embark everyone since the beginning, probably because there is still a little bit of R&D, so there is risk to be taken. It's not everybody will win, not everybody will have the right technique, and probably it's good to really promote all the possible effort of public-private partnerships that are possible. I don't know, so for in the European Union, you have a lot of different possibility. You have the European Institute of Technology, you have the Horizon Europe on the framework program offer a lot of possibility to involve public and labs and private companies. If you look in France, also our public research organization are really extremely happy when we start to propose a public-private partnership, even at small scale, because it will really lead to innovation. Even if it doesn't bring the unicorn in the end, it's still really promoting both research on technological innovation.
Paul, apart from LNG, of course. But
Yeah,
this time not
exactly.
LNG.
Everything I say now is going to be very self-serving. Yeah, we need more data. We need more Queen Mary researchers to collect more data. No, I think probably the thing that I find most exciting about some of the stuff that we've heard today, I think the sort of the technology testing, the stuff that that Tanya has been talking about. I think this project, so really doing a robust and independent assessment of the different types of technologies that can be used to quantify and detect. I think that is absolutely vital because, as I think has been mentioned a few times, the developments in technology is pretty quick right now, and it's producing a bit of a mess in terms of awareness from a company perspective. How are companies supposed to, especially smaller companies, how are they supposed to really keep abreast of what's the best technologies to invest expertise in, or to, what to do? And I think this type of project is going to be so useful in terms of raising the awareness of methane emissions and of technologies. Yeah, I think that's probably one of the most exciting things, and also, and obviously, like the chaps before me have mentioned, I think data collection is obviously a continuing battle that's really required. But I think the role of technology comparison and sort of publishing that stuff to raise awareness for the companies, I think is a really important aspect here, and that's definitely a role that GERG can play.
No, but this fair comparison of the measurement techniques, this was so essential, and I'm so happy that this has happened already. That moves us forward a large distance to where we need to be.
I think it shows that as gas companies, we are really willing to do something to reduce methane emissions. And so Tanya, I'm going to give you as the word as last, because we have already done a lot. And what do you see that we do more?
No, I fully agree with my friends. So we really need more researchers. So we need the scientists to support us. We need the European funds for carry out more projects, because the industry cannot do all this alone. And so I think that now the next phase of the GERG project, working on the reconciliation of the bottom-up and top-down approach, so that will be key for the industry, and also to continue working on the reconciliation factors, emission factors, and gathering more data to improve the accuracy of the data. So I think that that's my final thought on this.
And now, conscious of the time, it's already 3 o'clock. Normally we should have finished by now, so I'm going to thank my panelists. It was a very interesting discussion with all of you, and I had a lot of questions, more to follow-up questions for this, and I would have loved to ask them, but conscious of the time, I see that Maurice has put his camera on. Yes, Maurice, sorry, I'm too late. Just to wrap up, and very quickly to wrap up this day, it has been very interesting. I was really proud that I could present the roadmap, the methane emissions roadmap that has been developed by GERG. I think it was also important to show you that yes, we have already worked on it. Yes, we are willing as gas companies, as members of GERG, to go further, to reduce these emissions. Of course, conscious of cost effectiveness, I think this will be very important. Also, in the future, but certainly to go further with that. And yes, there is still a lot. This is a research conference. There is still a lot to do on R&D. And also working together, all together, because if we want to get there, there will be a collaborative effort that will be needed by all of you, all of us, in order to achieve the target. I will be really not longer than this. Going to pass the floor to Robert and Maurice. I don't know in which order you're going to intervene. And sorry that I've been too late with my second panel, but it was really too interesting to interrupt the panel before.
Oh, great! Thanks, Berenice. You've been a wonderful host. I think that the different panels were really great successes, great interaction, and it's really great to feel all the enthusiasm. And I think on everyone's side, on the researchers side, on the industry side, and other stakeholders. So indeed, there are challenges, and I think that what we heard is that those are numerous. This is a new facet, as was explained before, of an activity that has been going on for decades. And well, if there are new challenges, GERG is together with other associations, ready to pick them up and work out R&D aspects according to the roadmap that all of you have helped to develop. And also the criticality of bringing together data, and how such data can only be brought together with collaboration. I think many of you highlighted that, and I think we have lots of things to do. And well, in the interest of time, I'll hand it over to Robert. And probably, if some of you would like to hang around afterwards for a chat, I think that's possible.
Thank you, Maurice, and thank you everyone, and thanks Berenice for moderating today. It's been a long day, but it's been a fascinating day, and it just shows that there is so much focus. I listened to what Robert was saying. Focus on the science. Proper measurement is what we need. There's a lot of unscientific stuff out there, and we need to make it more scientific, and I think that's where we are going, in a very collaborative way. It's been a really good day, and thank you everyone for attending. Thank you everyone for speaking, all those speakers that responded so positively. The other thing that Tanya says is you can't manage what you can't quantify, and I think that's another important aspect of what we're looking at here. We do need to quantify better. We're moving with our roadmap towards the ideal of being able to quantify emissions better, but ultimately to reduce them. And as Paul said, we're looking for easy wins, but we're also looking to make the not so easy wins easier, and ultimately aim on that road down to reducing emissions by understanding, measuring them, and then mitigating them. And our roadmap is what we feel from a research perspective is the way forward, and that will be published later today. The brochure, at least the summary, will be published later today. The full roadmap will have to wait until after the 14th of December, when the European Commission publishes its legislation document. Yeah, ultimately, what I'd also like to thank, this is really important, I think Miguel, Magdalena and Alexandra should put their cameras on now, please. You're still there? When you switch your cameras on, thank you. That's one of you. Where's Alexandra and Magdalena? Thank you. I just got to say, I'm so proud of these guys, the work they've done over the last few weeks, months actually, to bring this together. They were convinced they could do this. 3 days of conference, we've seen one so far. The amount of effort that's gone into this, and you wouldn't believe well, you've all been harangued by these people over the last few weeks to produce your to say yes, and then to produce your talks, and to fit into the agenda, and it's all taken shape, and we've got 1 day down, and I think we're all very relieved that it's all happened. But I extend my extreme gratitude to the three of you, because you've let me sit back and let you do it. You were convinced you could do it, and you did, and we have 2 more days to go, and I'm sure the next 2 days will go just as well. So thanks. I'd like you all to thank the 3 members of the Secretariat who've done much of the work in bringing this all together, and also producing the documents that you'll be seeing on the roadmaps over the next few days as we publish them one by one. So it's a great team to have, and thank you, and once again thanks to everybody, and let's all collaborate, let's all work together and get these roadmaps running and moving forward, and get the get to where we need to get to, and start developing those projects. We need to get some projects running. You're all welcome to be part of the community. It was good to see Paul Balcombe end with Queen Mary University on the slides. That's where I started, in the Mile End Road, and spent 6 years doing research there. So I agree, Queen Mary needs more researchers. I'm one of them. I'm not volunteering, but it's good to see, and QM should join GERG. I think that would be even better. So thank you again, and you're all welcome tomorrow and Friday. We have a day on biomethane tomorrow. On Friday we have hydrogen. Same time, same place, same channel. You all got the links, I think. So please feel free, and you're welcome. If you have the stamina for 2 more days, I'm sure they'll be just as interesting and just as valuable as today. I'm not sure how we as the Secretariat will bear up to the load, but I'm sure the engine room will keep running in the background there on zero emission fuel, of course, and we look forward to seeing you tomorrow. Thank you.
Well, let's thank also Robert, because well, at the core of the Secretariat, doing with the team a great job. Many thanks, Robert.
Thanks, Maurice.